Okay, welcome to day 4 of second week in ST4 2020. Our first speaker of the day is Parthiv. He's going to continue telling us about his matrix bootstrap. Over to you, Parthiv.
Oh, okay. Let me just start by revisiting what I did last day. So basically we are trying to just, so I think I'm audible if I'm not wrong. So we were trying to understand some non-perturbatively some quantities related to the scattering amplitude. So we last did this double spectral density rho st, which is, just for sake of completeness, just me write it once. T is t equal to imaginary of t imaginary of s t is t, where imaginary of what it really means is that imaginary meaning taking say imaginary of ST is limit epsilon tends to 0 plus 1 by 2i t is plus epsilon t. So and likewise for imaginary of t, imaginary with respect to t. So this is we introduced because okay, and first also to write the K4. K4 was essentially, expression for K4 is (4 pi 3 by 2 gamma of 1 half plus infinity Tn and set delta plus delta plus minus so this was K, and K4, K4 in the expression of K4, you can analytically continue K4 in Z. But anyway, we will focus today more on this integral because this is going to be an important, this is one important stuff for whatever this non-perturbative kind of understanding, or that the analytic understanding that we are trying to do. Okay, let's go to the next slide. So what was that? 55. Okay, fine. So what we will do, we will now do these two contour integrals. So what we'll do, we'll do these two contour integrals by usual contour deformation argument contour deformation argument that we followed in derivation of FG formula. FG formula. Okay, the first order formula. So what we do, let's look at the integral once again. So I'm going to the previous slide. So I have this so there are two integrals. One is on with respect to eta prime and eta double prime. Now the imaginary of t will not I mean, when you take this imaginary of t, and I will write some explicit expression, what will be imaginary of t of this K4, that will be analytic, that won't have any problem, I mean singularity branch point structure for eta prime and eta double prime. However, as we already know that this t plus and t minus will have a branch point structure or branch point structure for eta prime and in eta prime variable and eta double prime variable. So what we mean to say is this, that if I look at, so I've gone to the next slide. So if I look at an eta prime complex plane.
Parthiv, can you go back to the last slide once again?
Yes. Yeah.
So this K plus expression, this expression you are K4 was function of z eta prime eta double prime.
Yes. Yeah.
And what you are doing here, the integration is over eta and eta minus z.
Yeah.
Okay, so
right,
only for the first variable the integration is there. Okay.
Yes. Yeah. Okay. So yeah, where was I? Yeah. The next slide. Okay. So in the eta prime complex plane, if I look at this t plus s eta prime function and looking for this t plus eta prime function, then of course s is there, but in eta prime there will be like branch cut structure, the usual branch cut structure. One corresponding to eta prime plane, another corresponding to of course the right hand side kind of stuff. And we will do, and similarly we will do ultimately, and deforming the contour integral for that, for eta prime, we will deform the usual way. That means we will deform it to this kind of contour integral. Of course, assuming that the contribution from the infinity contribution from the infinity can be dropped off. So that is what an assumption that we are taking. But you see, this thing actually here is more straightforward, because here so because here really, so I'm assuming that that thing actually goes away. So if I continue this stuff, if I do this kind of analysis, do this kind of contour deformation along the same line, I will reach of this form. So suppose the initial contour was something like that, and then you have deformed something like that. So something like that. So this has been deformed to this kind of contour using the analytic structures that have been already been used, a similar kind of deformation for the Schwarzschild formula. Once you do this deformation for both eta prime and eta double prime, what you will result on, I mean, the ultimate expression that you will land upon. So I'm going to the next slide. Is this rho st, the usual root s 4 pi square T. Plus multiplied this continuity of this is so okay. It's confusing. It's basically, I should say, just eta prime where the subscript actually represent that with what variable, I mean with what variable I am taking this discontinuity across the cut. And for this discontinuity of Z, I'm interchangeably using Z and T. So just to so let me give you this form of discontinuity of Z, which is very straightforward to calculate from the expression of T4. This is straightforward algebra. So discontinuity of Z is like this. Now, this has an important consequence is that this this is a step function. What this really tells you is that this eta prime and eta double prime integrals will be actually restricted in a sense, because I mean, non-zero contribution will come from a restricted region in a constrained region in the eta prime eta double prime frame. So just in the plane. So suppose I draw of course, the integration starts from Z0. This is the threshold point. But we will also have, so this step function is important. This step function tells that this, so what we will need that Z has to be greater than eta plus. And recall eta plus was actually a function of eta prime, eta double prime. So what it really means that the constraint becomes then plus eta square minus 1, eta prime square, eta double prime square minus 1, half then Z. So the integration region really ultimately becomes something like that. So this is that curve that defines this blue curve defines this constraint, that this boundary of the constraint, that this is satisfied, and the non-vanishing contribution comes only from this region.
So Parthiv, just to confirm, the region of integration is entire Z plane, right? And
yes, and
the blue curve that you are drawing, so that is bounding what?
No, so for example, so we are integrating over eta prime and eta double prime.
Right.
So without mentioning this discontinuity of Z, it's just because eta prime is varying from Z0 to infinity and eta double prime is varying from Z0 to infinity. But within this discontinuous of Z, there's a step function sitting. So this step function Z minus eta plus. So that step function will be only non-zero for Z greater than eta plus. So that restricts a region. So that will definitely exclude a region from the eta prime eta double prime plane. And only this this yellow crossed region is the one from where you will get non-vanishing contribution for the rho st. So simply speaking, when this so rho st will be only non-vanishing when this from this integration coming from this colored region from in the eta prime eta double prime. So does it make sense?
Yes, yes, okay, thank you.
Okay. So this is actually is very important because okay, so we need to some more work to see why it is actually important, a little bit work. So Z naught, just to remember that Z naught, expression for Z naught is equal to S minus S plus 4m square S minus 4m square. Okay, now what we will do, okay, so one thing is that that you have to understand that. So let's look on this relationship on this. So let's look on this constraint. This constraint a little bit more closely and try to see what does this constraint is telling us with respect to Z. So ultimately, rho S is a function of S and Z. S we have restricted between 4m square and 16m square. So that is the elastic entirety region. Now we want to understand in this with respect to Z what is the structure, what is the analytic structure of rho S. Okay, so let us do that. So I'm going to the next slide, slide number 57. So Z has to be, Z is equal to, so basically Z is equal to 1 plus 2t by S minus 4m square has to be greater than eta plus, but eta plus is a function of, eta plus is of course is a function of eta prime, eta double prime, but the integration domain starts from, it starts from in Z, eta prime equal to Z naught, eta double prime equal to Z naught. So Z must be greater than eta prime Z naught Z naught, where eta prime, sorry, eta plus Z naught Z naught is equal to two Z naught square minus 1. So if you, for example, you simplify this, when you put the Z naught value, you will find out 1 plus 32 SM square S minus 1 square whole square. Now, if you replace this Z in terms of, so recall Z is in terms of 4m square. If you manage this thing, what you will find out is that the boundary. So what we obtain finally is that the Z has to be greater than 4m square. The boundary, that means when, so Z has to be greater than this. So the boundary is of course Z equals to 1 plus 32 SM square S minus 4m square, and this in T plane, in terms of T, this becomes m square. So in ST plane, this is known as Landau curve. So in the ST plane, this is known as Landau curve. So why Landau curve is important? So if I try to look from the ST plane, or from in the ST plane this similar situation, then what it really means to so let's see. So what it really tells you that T has to be, in the S channel, what it really tells you is that in the S channel, the T has to be greater than this S channel unitarity region, that means 16m square by 4m square, T has to be greater than this Landau curve in order to be in order that rho st becomes non-zero. A similar expression will a similar Landau curve is also there in the crossed channel, that means in the T channel. So that will give me this kind of diagram. So go to the next slide. So let me draw this diagram. This is an important diagram. This is T, this is S. So start from 4m square origin. This is 16m square. S channel, T channel. And so this strip is the so for example this vertical strip is the elastic strip for the S channel, and this horizontal strip is the elastic strip for the T channel. So there is this is the S channel Landau curve I just told you, and there is an analogous curve in the cross channel. So just to notice that this whole region is the multiparticle region, because from here this green shaded region is the multiparticle region. So this is outside the elastic unitarity. Region goes, and this crossed region in the region where rho equal to 0. So in the ST plane, this is important. So this is my T equal to 16 S m square S minus 4m square. The blue curve is T equal to 4m square S minus 4m square. Sorry, 16m square. So what this graph actually tells you is that how this rho st behaves in this ST plane. So this red curve is one what is known as the leading Landau curve, and this green curve is the leading Landau curve in the S channel. The green curve is the leading Landau curve in the cross channel, and it is the blue curve. The green shaded region is the multiparticle, so from where that multiparticle unitarity will kick in, and this entire this cross sign region is the where that rho st is actually 0. So this region is also called as some Steinmann shadow. So for our purpose, we see that within the elastic region, that this small region between this within this elastic strip in this channel, which is this blank white region, is the one where there will be contribution. And similarly, from the T channel elastic unitarity in the cross channel elastic unitarity, there will be this region will be there. But most importantly, suppose you so for example, if you go near to the this is a non-partitive structure of the rho st function that is we obtain from this elastic unitarity region. I mean, it is this constraint that this rho st is 0 in this kind of elastic domain. This is an important constraint. And for example, why these recent studies were done on identifying this kind of stuff is it is important to impose these kinds of constraints in the numerical bootstrap studies where these kinds of constraints were not previously considered.
Parthiv,
yeah.
Probably I have not understood all the regions. So, like whatever you were telling, this below this red curve, all the regions are not allowed by S-channel scattering, or the rho will vanish below this red curve.
Yeah, rho will vanish. So for example, rho is vanishing. Yes. So
below the red curve and also below the blue kind of curve, right?
Yeah. Below the green curve. So the point is that so red curve is, you see, this red curve is also extended. Of course, it is extending into the multiparticle. I mean, when there is a multiparticle unitarity channels also. Okay. Similarly, green curve is also going away from. I mean, it's going out of the elastic channel and going into this multiparticle unitarity channel. So if you are just focused on, so important point is if you just focus on the elastic strip, like the elastic unitarity region,
right.
Then down the red curve, there is actually in the elastic region there is no rho st is vanishing.
Okay.
Within the elastic region, where rho st is non-vanishing, is this one is above the this red curve. So it is this white region is the topmost vertical white region.
But this is not allowed probably by the blue curve, right? Means I think you are telling that there is some contradiction or not?
No. There is no contradiction. So for example, the point is that okay. So the thing is that so this is allowed by the blue curve, but with respect to blue curve, you have to see. So whatever I've just told you is that it is this crossed region which is where actually rho is equal to 0. Okay. And this actually follows when if you look at the, okay, so let me just go to the other. So it is one Landau curve. This is actually with respect to S-channel unitarity Landau curve. But if you also see from the T-channel with respect to the similar kind of Landau curve structure,
okay,
then you will find out that region. So for now we are interested into, for example, S-channel. But one beautiful thing is that you see, so beyond this S-channel unitarity region, there is some region will be there, which will be related to T-channel. Which will be related by crossing to the T-channel unitarity region. So what I mean to say is that so beyond the 16m square line, there is some region in this with respect to S-channel multiparticle region. This green dashed line. That can be related to this region within the T-channel unitarity, this white region. So in that sense, if you are looking at S-channel, you can apply crossing to go into. So if you just derive a formula for let's say you derive a formula for elastic in the elastic unitarity region, then you just apply. But if you really want to see that, okay, can I, whether this formula can tell me anything about beyond the elastic unitarity region or the non-elastic stuff? Then what you will do, you can use a crossing to go to T-channel elastic unitarity and use that to constrain some inelasticity in this channel. So that is one idea.
Okay. Yeah, I understood.
Okay. So this is actually so one point is I think in this recent works they all try to understand this kind of rho st analytic structures. Of course, it is not clear at this moment that what you can do with these structures of this kind of analytic properties of the rho st, but these kind of it seems a patchy work in the sense that they seem to be very disparate works. But I will see at least one application of this kind of analysis to this large spin expansion kind of stuff. But they all form these small bits of this analytic bootstrap that these people are trying to explore. And of course, everything needs to be streamlined. So currently, this seems like separate information. But how to streamline all this is an important point that you have to understand. Okay. Let me go to now second, to the core of the problem that I advertised last day, is that regarding the large spin expansion of the stuff. So, okay, we go to the next slide. So, large spin, of what we are attempting to do a large spin expansion, we are attempting to do a large spin expansion of the partial wave coefficient. So, let me write down this partial wave coefficient in the Frossard-Gribov formula, which is and we also obtain that the real L is greater than some J0 something, and this was, I guess, 16 pi or something. Now, the large J behavior of this QLZ is given by, so this is actually so let me say large L behavior of QLZ. This is given by of this form. This form. With where lambda z is that's minus 1, square root of z minus 1. Of course, mod z is greater than 1, and yeah, mod z is greater than 1. So what it really tells, essentially what it tells you that, for z greater than 1, lambda QLZ in the larger limit decays extremely fast, because it's an exponential, because the key point to understand is that this thing lambda z minus L is essentially lambda z, and it's square minus 1, so it's essentially of this form into a minus LZ. At least that is the leading kind of stuff, 2LZ. So what it really tells you is that it decays very fast for large L. If you the more you go to the more you increase the Z. So what does it imply is that in the larger limit, this integral will have its dominant contribution from this lower limit, Z0. So near the Z0. So it is this near this Z0 or the threshold that will give you the dominant contribution in the larger limit. So let me just write it down, that in the larger limit, the dominant contribution will come from the lower limit of the above integral. So what does it mean? We have to consider, the property of this TTS and Z as a function near this Z0. So we need to property. So Z0 is a threshold. Remember, so this is the threshold. So we need to understand the property of this whole stuff near the threshold. So what we need is the next slide. So what we need is to understand property of TT is set around the threshold Z0. And there is an answer to this, which is known as which basically goes by the which basically goes by the name threshold expansion. So this goes by the name threshold expansion, where the parameter is so this is essentially gives you so this kind of threshold threshold expansion is what we will need. So what we will need an expansion around sigma is equal to 0. So this is what we are ranging for. So just to tell you this thing, that this kind of expansion is known in nuclear physics by the effective range expansion. It so happened that in the when sigma is when sigma is very much less than 1, it becomes some non-relativistic kind of stuff, and then it can be then you can have an effective potential kind of stuff and something like that. So it's a very interesting thing that you are doing this threshold expansion, and in a sense this expansion is a kind of a low energy kind of expansion that we are trying to do.
I think probably I missed some point. Maybe like you are trying to understand near Z equal to Z0 contribution, because there you are telling that only large spin will dominate. And why not the other points leaving the Z0, because their small spin can also contribute. So
so let me go to the previous slide and point it out. So so we are trying to see this, because since we have a spin, we can try to see and what kind of large spin part of large spin expansion that one usually does in the TFT bootstrap kind of stuff, that in 1/L expansion. So we are looking at this large spin, large L behavior of these functions QLZ. And as you can see, let me just point out, maybe I just don't point out enough. So essentially, the large L behavior of the Z is it's very exponentially fast decreases from at the very large Z. So when you are considering, so here we are our first point. So our first starting point is that we are looking for large L behavior. So we want to do a large spin expansion. That is why we are looking for a large L kind of behavior. Of course, the truth is, of course, ultimately we would like to do for small spin. And in fact, a small spin you have to do stuff kind of resummation and blah, etc.
But I mean, just trying to ask that like, because this basically, if you want to find the amplitude or the discontinuity of the amplitude, you need all the FLs for all values of Ls.
Yes.
But now just you're trying to get only for the large values of L what will be the FLOB, and you're telling the near Z0 only if we take consider
right,
discontinuity, that would be enough.
right.
But to get the amplitude, probably you need all value of L to sum over.
Yes. Of course, we get actually all the value, and most importantly, even experimentally, also you only what people actually see is the small L values like L equal to 0. I mean, out of this FLs, people construct like S wave or D wave scattering lengths and so on. I mean, but this is also in spirit of what the people do, this kind of large spin expansion in for this OP coefficients in conformal field theory. But there also, ultimately the issue comes, and how can you I mean, large spin expansion really works for large spin, and the question is that to what extent you can extract it to a finite spin, like finite small, maybe finite spin. That's a good question. But here we are, and that is also always the pressing question. Even there, it will be also the pressing question even here. But only that at least here, this analytics is still not known. So it's this, what I'm going to tell you is still incomplete, because then you have to do this thing properly. Yeah, just to make the.
Okay, thank you.
Yeah. Okay. So this
Parthiv, in your next slide, in this slide, what is the relation? I'm in slide 60. So I'm asking, what is the relation between this threshold expansion sigma s that you introduced and the Z0?
Oh, okay. So this I introduced in a so for example, this I introduced in this sigma s kind of expansion in S channel, but Z0, you recall, Z0 was in basically T channel. So you will actually use a threshold expansion in T channel. But how do you know that, if starting from a threshold expansion in S channel, you can go to a threshold expansion in T channel? That's because you can you are going to use the crossing symmetry. So that's how you're going to relate this to the using crossing, and that formula, you're going to relate the threshold expansion to the large L expansion. That's the logic.
So when you will carry out the integration, I mean, is it that contribution will come from sigma s equal to 0 or around sigma s equal to 0? I'm a bit confused here.
No. Okay. So that contribution will be coming around of sigma t from around sigma t equal to 0.
Okay.
Sigma t equal to 0, because just sorry. Yeah. Even I also confused you. No. So for example, so let me just write down once again this. So Z0 was S plus 4m square by S minus 4m square. So as S is so when S is closest to 4m square, this Z0 is extreme. So Z0 formally goes to infinity. Like if you just put S equal to 4m square. But what I try to mean is that as S is, S is not very different. I mean, S is small compared to 4m square. This Z0 is very large. I mean, this lower limit is extremely large in a sense. So that is where from you are getting that, you are going to you are focusing on that sigma s expansion first.
Okay.
Yeah. I'm just saying that, these ideas it's just introduced. So I think they will be even more refined as the time goes. But I'm just showing you the recent glimpses what have been attempted at least. Okay, so to have this thing, that is to proceed further, what we'll need, we are still in the, so we need to use the consequence of, so need to use on the partial wave coefficients. Okay, let me go to the next slide. Okay, so just to remember that the unitarity, and this is unitarity has this consequence on the partial coefficients. If you take into account this full unitarity constraint, I mean, then this so they have this FLS is actually turns out to be greater than equal to S minus 4m square by S half FL square, FLS's mod square. So this actually follows from the unitarity equation. If you just do project the unitarity equation onto, I mean, the whole unitarity equation onto the angular momentum basis, you get this kind of equality. The equality stands for only elastic unitarity region. So when 16S is in this elastic unitarity region, then we have, so this imagine with respect to S is equal to then you have this equality. So in the elastic unitarity region, you have this equality. And using this, one can, so what one does that if you take this FL square in a downwards, divide both on side FL square, using this one can actually show that this has the form where PL sigma S is real analytic and single valid. In a small z. Okay, so so that means you can write this 1 by FLS as equal to BL sigma S minus I by 2, and this in this form. Where you see I have explicitly expressed it in terms of sigma S, which is basically this proportional to this ratio S minus 4m square. Now we will
Sorry,
need.
Parthiv, so the earlier line was really a nonlinear equation for FLS because there is mod square in the right. But the second equation, whatever you have gotten, roughly if you just like inverse it, it will become a linear kind of wave in FLS, right?
Yeah.
So have you make it somehow linear? I think it could be make linear by taking mod of FLS kind of thing, and then BLS. Sorry, yeah.
Sorry, where? So why are you saying no? It's second line meaning this 1 by FLS A.
Yeah.
This expression. Okay, yeah. So it's basically so let's be thing. So if you divide on both sides, so let me just write it. But what you get from this equation, what you get if you divide on both sides by this mod of FLS square, you can actually obtain from this two imaginary of 1 by FLS plus epsilon equal to minus S by 4m square plus half. Yeah. So what you just do is that if you basically divide on both sides by this mod of FLS square.
Okay.
And then you for mod of FLS you just write down properly what you are thinking, and then you can get this expression. And this red box is basically a solution, a kind of solution to this.
So
now,
BL sigma is basically kind of, you are telling the real part of 1 over FLS.
Yes. Yeah. Kind of. I mean, okay. So yes, it's but also it's real part, and also it's almost, I personally suspect. So let's be honest, because I do not. So if you put this form in, if you put this form of 1 by FLS into this expression, this matches. But I have not been able to see a derivation, because I have not also seen a clean-cut derivation from, let's say, starting from here to this red box. And I have also failed to do a systematic derivation. So yeah, I suspect maybe some kind of integral derivation, can be given. But yeah, I have not still been able to do it. Just to be clarified.
Okay. Means your BL sigma is still undetermined. This is what I probably want to ask.
Yes, no. So BL sigma is BL sigma is, we are going to we will tell you about some form I'm just going to tell you about BL sigma s.
Okay, sure.
Yeah. Okay, so we will still need to know about this, just like this BL sigma s. So okay, so I'm going to slide 62. Next slide. So BL sigma s, actually, this can be shown that as sigma is going to 0 plus, this is okay. Then so there's this definition called scattering length, which is defined like this. So scattering length is defined as FLS S minus 4m square minus 1 or L so this is what they this is what is known in the literature, this particle physics literature, as the scattering length. And so I have talked. So what is the, if you ask me what is the physical significance of the scattering length? Of course, this kind of quantities are considered in non-relativistic quantum mechanics, and they are in non-relativistic quantum mechanical aspect. They are really they are really a quantity for measuring kind of Hart sphere potential. So what kind of phase shift of a spherical wave that is going to reflect it from Hart sphere kind of stuff. So as I have understood from talking from experimentalists or so, these are kind of measure, because we are talking about, essentially a low energy kind of scattering, because pion scattering, low energy pion scattering. So these are basically low energy data, which tells you that, how can you approximate the interaction by an effective potential kind of stuff. So yeah, in the experiment. So this is this is an experimental observable that experiment is actually calculates. If you open, for example, particle data book or something, you will find out values for this quantity. So what is the important point is this, that there's this thing that this, so people actually assume that this thing is finite. So assume in the sense, why it's assumed, it's, no theory proof. Of course, you see it in experiments. You find out. I don't know how they calculate actually. So because anyway they calculate how they construct these quantities from cross sections. So I do not know the details. But if you see, these are all finite values. But I think in theory, there is no priority of saying that why this is this is why this is finite. So they assume the finiteness of this these quantities. Why introduce these quantities? Because this BL sigma s, this I just told you, this BL sigma s, they have this structure, they have this asymptotic structure as sigma s goes to 0 plus, as AL sigma s L. And this actually can be seen from the Frossard-Gribov formula, at least that's what. But frankly speaking, I do not understand this point very much. So you can just have to just take it as that form. So what they demand is this is from the Frossard-Gribov formula that this form actually follows. But you can work with this form. If you are working with this form, then we are sufficient to go. But how it forms clearly, it's not very clear to me, and I don't think it's the analytic thing is also not very clear for that matter. Okay, if you consider this form, so especially this BLs sigma s are taken of this kind of, this is FLS. One minus L, where of course L is assumed to be greater than 2. And this L is greater than 2 factor really comes from the fact that we are assuming that the Frossard-Gribov formula actually works for spin up to 2 from onwards. But that would also mean that the Rege bounded, so that Rege power is less than 2. So for example, L equal to 0 is a particularly nasty bit, because this we do not know, because for L equal to 0, clearly the Frossard-Gribov formula actually does not work. So since it does not work, for L equal to 0, you cannot write down this kind of an expression for BL. Still, you can, if you take a Q, you can still try to write down an equation of this form. J naught B0 I. where J naught is now of course unknown. So J naught is some unknown constant. Why J naught is unknown? Because when you try to apply the Frossard-Gruber formula for spin 0, L equal to 0, you essentially you have to consider that contribution from arc. So that arc contribution you need to know. So it is that piece which is missing, and it is this. So I suspect that is that arc contribution. If you try to take it properly, that should give you this understanding of this. So let me just this J naught tilde. J naught tilde. So this is the J naught tilde. So this amount of structure, this structures of VL is the last piece that we need to write down the a kind of an expansion. So the kind of threshold kind of expansion that we are heading for. So let me just write down the quick expression and then just stopping for a moment.
Parthiv, I have a comment. Like
yes.
Like when you are showing the dispersion relation in the S channel, you are telling that it was going like S square. So you have used two subtraction scheme to expand in the polynomial, and then starting from the square, you are doing the dispersion relation. So here, suppose in the T channel, it goes like suppose Z to the power J0, and J0, like you are telling that it starts from say 2. Kind of thing. That's why you cannot allow L to be less than 2. So here, can one use the same kind of subtraction kind of thing in the Z variable to write down the dispersion relation, and then possibly can one?
Yes, I think so. I mean, I have not seen any I've not seen any dispersion relationship in Z, but yeah, I guess that's perfectly valid the way you're saying. Yeah, one can think that way.
Okay.
But I think this is a problem with this FG kind of formula, that they are never valid for this small, because in doing so we have taken care of that, that because because one of the main point was that there was this in FG formula, there is this QLs are going sitting around. So that has to be taken care of, which is, for example, in the usual dispersion relationship, it is not there. Like there's no extra QL power. There's just T, TS 1 by S something. That has to be balanced.
Yeah. Okay.
Okay, fine. So okay, so let's So if I do this, I will get an expansion of a threshold expansion for imaginary of Fz in this form. So let me just write it down in the next slide. So I've gone to the next slide. Imaginary of FLS. Equal to 4m square sigma s square sigma s 2 root s half PL square sigma s plus 4m square sigma s 4s minus 1. Of course, we have constructed it in the like 1 by imaginary of FL, so we have to just invert it. So this is the final expression that we are going to use in the. We are going to plug this expression into the using crossing into to obtain that large Z. So what the selling point of this expression is that it's an expansion around sigma S equal to 0, where we are getting the dominant contribution in the large L expansion. So this expression is the one that we're going to put in the large L in obtaining the large L expansion. So yeah, so let me just go to the next slide. Okay, if is there any question before just write down the stuff in the large L expansion. Okay, if not there, then we just go to the last bit of large spin expansion. And if you do this large spin as approximations for this Q function that I just wrote you in a particular way. So here, of course, you see Z is around. You take this. You take this small deformation around Z naught. Then FLS can be written proportional to some factor where you integrate E delta Z, but e to the power minus delta Z expansion, and this is S T delta Z, and of course there will be an L function because we have expressed this. So now, just as I was considering sigma S, you can consider here sigma T. And if you consider the sigma T, that means that difference, write down the sigma T as like that. So what we do ultimately, we can use this form, this. So what we are going to do is that we have derived this imaginary of S with respect to imaginary of FLS with respect to S, and what we can do is we will use the crossing, that means S going to T in that expression, and putting the crossing we can obtain this imaginary of T of FL. So imaginary of S FLS, you use the crossing, and then from there you get imaginary of sigma T. And that stuff, that part you incorporate in this integral, where you actually express everything sigma T, everything else. So for example, in writing this T, you express it in terms of a partial wave expansion of like partial wave expansion, where there is sum of imaginary of FL T. So is this point clear? Like that. Is there any question? So I know it's a fairly technical point, but yeah, so that's how you have to go. So if you do this calculations, ultimately, what you reach is so first I would like to say that these are all leading singular kind of behavior, and also this 1 by see there's this systematic 1 by L correction to that QL formula we are going to have. So finally, if you are going to have this, you are going to have the final form as, to do all the calculation, you're going to have the final form as, well, S is proportional to, let me just write down the most important point, L half so the important factors are this. So there's a so the leading term comes out to be 1 by square root of L, and the S dependence is entering through this. Of course, this it is this combination, which is actually you can try to compute where Z naught is really S plus 4n square minus S minus 4n square, and this one there are 1 by L corrections. So this is the leading behavior, leading one by large spin behavior, or large spin expansion kind of stuff for the partial wave coefficient. It's almost in the same spirit as the similar kind of large spin expansions are done, for example, in conformal bootstrap program. So I'm trying to emphasize this because this parallelism between this conformal bootstrap program and the S-matrix bootstrap program. This is because to a large extent the current attitude is to take a kind of an inspiration from the formal to try to apply to the second. So of course this is a large L. This is a large L behavior, but important is that you ultimately, if you want to really to make something at the experiment, you would like to understand small L. So for example, finite L stuff. So that is actually a problematic point, and how to make sense of this finite L, how to come to this finite L, or what can be extracted for finite L, which is still unknown. So let's just say that which is still unknown and still not clear. So this is just one method and procedure, and let me just tell something that there's similar thing you can also calculate for imaginary of FL, imaginary of FLS. The similar analysis you can try to do, only there you will need a threshold expansion of rho st, that the double spectral function that I discussed earlier. So from this rho st, you can also consider this imaginary of FLS. Why imaginary of FLS is, for example, interesting? For example, in forward scattering amplitude or something like that, it is this imaginary part which enters. So in these imaginary portions of the partial waves, they are of more interesting than the normal FLS kind of structure. So this is what you can say. This large spin expansion is the one which so this is this kind of new result in this new bootstrap program. Of course, this whole analytic studies of this bootstrap program is it's still at a very early stage, very nascent stage, because almost nothing is done. Of course, there's a whole lot of old results, but the problem of the old results is that there are too many old results, and they have to be streamlined. And most importantly, what kind of useful stuff you can do with all this kind of stuff. Because ultimately, our goal is to make some connection with physical world. Apart from this abstract calculation, we would like to extract some numbers. So let me try to conclude this analytic structure, that what kind of problems we are interested in. One thing is that one can try to do this kind of analytic bootstrap of whether one can apply this analytic bootstrap to see some the kind of low energy effective field theory calculation people do in connection to, let's say, point-to-point scattering, like chiral perturbation theory. So one question is can one analytically, so let me just write down in a separate slide. So questions are there. So go to the next slide.
So Parthiv, before that, one question. Can you apply this bootstrap technique to get information about lower spin from the higher spin analysis that you are doing?
Yeah, I think this. So that is the one point. It's not clear still that how to get that. So that is ultimately that is the ultimate goal, that to understand this lower spin. So this lower spin, how to go to the lower spin. I think it will take a little more analytic results, analytic analysis, and we are also thinking about this, but still not. There's no. I cannot give you a definitive answer. I mean, what is the actual method? I mean, how to resum this stuff? We'll have to clearly resum this stuff in some way.
And another thing, is it clear that when you are dealing with this higher spin, meaning for large spin, only this two particle exchange in the intermediate state dominate, and the multi-particle channels, they are somehow not contributing, or at the leading order?
Yeah, I mean, yes, this
so
is actually
for lower spin, for small spin, it is still the same case.
No, as I'm saying that I think for high, so this asymptotically large spin, as you told, this unitarity, this elastic unitary region is the dominant, and multi-particle contribution will come as subleading. But again, the problem of this lower when it comes to lower spin kind of stuff, I do not. So I have not seen any so far. There is no definitive work. I mean, so for example, this work so all this thing is inspired by this Zhiboidov's recent work on analytic S-matrix Bootstrap, but even there they are not mentioning it. I mean, I really don't understand what they are doing actually when they are discussing this finite L, because it's not very clear that what they are trying to do. So I would say that no, it's still an open thing to actually understand this. Yeah, so that's an stuff.
Parthiv, I have a similar kind of question. Like you are telling that near S equal to 4m square, you are taking the discontinuity. But you have shown in the earlier one of the figure that actually even in the elastic region in the S channel curve, that if you use crossing symmetry, then it contains some non-elastic region in the T channel kind of thing.
Yes.
So actually, is it also taking care of multi-particle thing somehow?
Yeah. So actually, so for example, so the analysis that I showed right just now was the elastic. But interestingly, using that thing, so let me just go to, which slide is that? 8, just to point out. So in slide number 58, so for example, in the S channel, in this vertical, so in the vertical way that so it is that green shadow between this this vertical dot and the blue channel and this blue line, this is some inelasticity in the S channel. So interestingly, this inelasticity can be actually related to, so you can put some bounds on this inelasticity using information, I mean using this kind of expansion for that only in the T channel threshold expansion. So you can use the T channel threshold expansion to use that. So T channel threshold expansion meaning it's an expansion in this horizontal blank space near horizontal blank space above this blue curve. So you can use some kind of threshold expansion in this region to put some bound on the inelasticity in the S channel. Of course, some portion of the not the entire inelasticity. There is also a subtlety there. So more precisely, you can put a bound in the inelastic region for S greater than 64 by 3m square. This is actually purely due to how the Landau curves are this Landau curves are positioned, due to essentially how this happens. So there is an intermediate region where there is, where what happens is still an open question. So for example, there's an intermediate region between 16m square to 64 by 3m square, where yes, you don't know anything. But other than that, for S greater than 64 by 3m square, that is, if you want, that inelasticity in FJS can be related to a T channel elastic unitarity stuff. if that is your question. Yes. Okay, so just to mention, so just to give an overview of this thing, that all of these things are very still in a cluttered scenarios, because there's no full picture available still now, because so far whatever the S-matrix Bootstrap has been done, at least in the modern S-matrix Bootstrap, which are all numerical studies. I mean, they are actually computer codes and doing so. You see, only small portions of this, I mean, only recently there's this very analytic. Of course, there was this classic old results and old theorems are there, but how to use them to extract anything meaningful is a good question. But also you need to know some kind of what kind of meaningful questions you can ask. Well, one practical question is that can you do, for example, chiral perturbation theory using Bootstrap? Because chiral perturbation theory is a low energy effective field theory, often used to study this pion scattering scenario within the frame of QCD. But chiral perturbation theory itself is complicated. For example, even going beyond one loop takes quite an effort. So just like, for example, in conformal Bootstrap, people do these epsilon expansions, and even doing higher loop epsilon expansion is a very, in Feynman diagrammatics way, is very tedious. But Bootstrap has essentially reduced that. It has given this higher epsilon order results very simply using Bootstrap. So can you do a similar kind of stuff here as well, and get some numbers, that numbers which are actually in experimental numbers? Other kind of stuff, what other kind of numbers is, of course, is important is the Regge trajectories. So for example, the pion these Regge trajectories are actually, so there is no microscopic explanation or actual complete theoretical understanding that how to derive, for example, the Regge trajectory. So for example, pion Regge trajectory is drawn from experiments which has this form. Sorry, it's actually a nucleon of this form. So what is important to understand is how do we get these numbers? These numbers are actually these numbers are actually drawn from the experiments. So can one actually get these numbers, somehow out of Bootstrap? So that will be really very nice for that matter. And this is, I would say that it's a quite this will be quite ambitious of this thing. And last but not the least, and this is very important, of course, is another parallel, that we are missing a huge sector, that is how to do massless particles. And since we are missing these huge sectors, we are missing QED, I mean electrons, and then of course leptons kind of stuff. So the good question is of course, so the whole electroweak sector for that matter. Let me just electroweak sector we do not know. So we need to develop, of course, a full-fledged analytic structure and analytic understanding of massless particles, because only where it's a problem is that many of these glorious theorems based on which this for massive particles this program is built up, they do not work for massless stuff. So that one needs to understand that how to get these massless particles to get going of these massless particles. So these are the imminent problem that one should ask. But also even before that, I must say that this whole analytic program is still in a nascent stage. As you know, very few works are happening on S-matrix Bootstrap. But you will need, if you want to actually do something useful with this program, I mean, apart from some philosophical mumbo jumbo, we need to invest more on this analytic stuff. So by this I conclude the analytic part. I mean, in the next 2 lectures, I will mostly discuss the modern numerics, which will be, I mean, of course, I wouldn't be able to show you anything, but to show you the basic logic of the analytic stuff. So yeah, there I conclude this analytics structure for now. So I can take questions if any. The next 2 lectures will be most on numerics.
Yeah, so Parthiv, one very nice question, since you're talking about this massless particles, I suppose that apart from the pole structure that is, I mean, S equal to 4 and so that threshold, it also gets continuously distributed from the origin itself, so there are problems. But apart from that, from the loop amplitudes, meaning when we do these perturbative loop corrections, IR divergence issues appear.
Yes, that is also so.
And in your talk, like when you are talking about this analytic structures, nowhere you mention about any kind of loop corrections, I suppose. I mean, although you talk about this multi-particle exchanges, but won't there be issues issues like UV finiteness, meaning renormalizability and so on, appear in this structure, in this framework?
No, actually, see, this UV, so for example, the whole point of renormalization enters because ultimately in field theory calculations, you are you are doing this whole you introduce the renormalization and you cut off this upper limit of the integral, because in this whole field theory point you are doing this whole optional integrals. But I think in the S-matrix you do not have that kind. In that sense, you really don't talk about renormalization, because essentially nowhere you have introduced any off-shell kind of stuff. Even when I'm, for example, in unitarity, the only place I introduced this multi-particle intermediate stuff was in unitarity when I'm breaking that T bar T. So when I'm breaking that T bar T. So yeah, so in that sense, I do not think that unitarity, so that kind of loop. But what you were talking about, this IR divergence, I guess this IR phenomena will also be there, because I have not detailed study in the massless particles till now, but I was reading a paper of, I was reading an expository article of Chiu. I was reading an expository article of Chiu where he was mentioning that even this, just as a scattering matrix, that will also suffer from IR problems. So I'm not exactly sure what does it mean. So his point was that for massless particle, you really cannot talk about a finite number of particles, because you really don't know how to distinguish between 2 particles when both of them are massless. So essentially they're on the shell. So yeah, so I think that is one serious problem. Very recently, Matthew Schwartz has introduced this a new kind of, what he calls a hard S-matrix. I'm not very sure that whether that's going to play any definitive role or not. Yeah.
Okay, thanks. But your comment about this renormalizability, I mean, I don't know much about that, but the thing is that this way of thinking the S-matrix, that is from this entire on-shell construction. So do you think that this renormalizability issue or this UV divergences, meaning the usual way of dealing with the UV divergences, that are not required? Is that so?
Yeah. I mean, so for example, in this S-matrix setup, I've never seen this. Renormalization anywhere, because for example, this UV divergences usually appear because of your concern there's loops and all those, and then you are of course integrating all over this. All over the momentum, all momentum space. Then so far, I've not seen anywhere this terminology, renormalization, and all this kind of stuff in this construct. So yeah, that is, I've not seen anything.
Because you see that these masses that you are talking about, so these are probably the bare masses, right? And then when you in the field theory approach, when you loop corrections, I mean, you have to add the counter terms, and that also correct the masses and also the vertices and so on. Now, when you talk about the thresholds or the pole structures, they rely heavily on the masses of the particles. Now, what kind of masses actually is one talking about in this framework?
Okay, so in this framework, so for example, this framework is assuming that when the particles are scattering, like when I'm measuring them as particles way before scattering, or at least way before scattering. So when I'm seeing these particles, like I'm seeing these particles way before scattering, like when and way after scattering. So I'm sending off these particles to scatter, but they do scatter sometime. I do not know which time they're scattering, and then I'm collecting these particles at some point where again they are just essentially free. So I think so these are so essentially these masses are, you say, this mass of free particles. So I think that you do call like bare mass, I don't know, bare mass kind of stuff in the field theory language, because maybe
can I make a comment?
Essentially yeah.
I thought that the poles of the S matrices always appear in the physical mass.
Yes, physical mass. Yeah.
So physical mass
so physical mass are renormalized one.
Yeah, physical mass is not bare mass, right? I mean, it's after you have done all the renormalization. I mean, in the usual field theory lingo. So I think this S-matrix program, I mean, because it's evaluating the on-shell amplitudes or on-shell scattering, I think in some sense that physical renormalization data is already encoded. It's just not very clear that how exactly it is encoded. Because the way we are used to thinking about renormalization is very heavily dependent on writing down a Lagrangian and doing the usual thing.
Right.
So in some sense, are we already assuming that this UV finite theory already exists when talking about this on-shell S-matrix construction?
Well, I mean,
because as Shubhanin was pointing out that I mean, the masses, the poles are the physical masses, and the issues of renormalizability and so on have already been tackled. So that means we have a very good theory with all the finiteness. So that assumption, does it already go?
Sorry, it doesn't imply that it's a good theory with finiteness, right? I mean, when you usually even do the Lagrangian way, just because it is renormalizable doesn't mean that it is UV complete. It means that there is one energy scale up to which your theory will keep on giving good answers. But if you keep on pushing that energy scale to arbitrary, so even if you don't have any other energy scale, you definitely know that at the level of Planck mass, your theory should break down. So I don't think Parthiv, or I mean this S-matrix program is making any such claim that this theory is UV complete.
Yes. Actually, right.
Yeah. Please go ahead.
Actually, I have not. Yeah, I think I echo with Shubhanan to talk to that. I've never seen these terms like so these usual field theory terms that we say this like never into this. That maybe right. I think that is also why these people kind of try to build this thing that like to avoid those kind of stuff. So I do not know how the translation between field theory and these results, I mean, what would the exact translations would be. Like, that is, I don't know.
So in this framework, at what point are you introducing any energy scale? I missed that point. So, okay, if I understand correctly, when you say the thresholds, so those they introduce some kind of energy scales. Is that right?
Yeah, I mean, yes. So threshold is, for example, the first threshold. So first threshold is simply when that reaction can happen, like kinematically, kinetically, when that reaction can actually happen, because it's just 4m square. That means it's simply like it's like 2m square. So it's basically so it's like 2m whole square.
Right.
Now, so for example, the next threshold. So here I'm considering the Z2 symmetry. So next threshold appears 16m square. So there the condition is that in 16m square, what can happen is that so I'm sending 2 particles, but in the 16m square, there's a possibility of 2 going to 4 particles. So what it really means that suppose I'm sending here 2 particles, if I am sending it with the energy between the energy between 4m square and 16m square, then I will always get that 2 particle as a final state. But if I introduce more, higher energy, then I get more particles as an outgoing system. So now, of course, you can ask that what is happening in between. But I think the whole idea was like that: what is to capture what is happening in between by simply this consistency kind of stuff. So that's when the inelasticity actually kicks in.
Yeah, I see.
Yeah.
Okay, we are 5 minutes past 12:30. I think we should unmute yourself and thank Parthiv for this lecture. So, are there any further questions? Okay, if not, then we can pause the recording and then people can continue asking questions or discussion more informally. Okay, welcome back to the post-lunch session. Our next speaker is Pratik. He's going to continue telling us about tensor networks and related topics. Over to you, Pratik.
Okay, thank you. So today I'll be discussing these topics, multi-scale entanglement renovation answers. So we'll start from where we ended up last time. Okay. So we have seen this disentanglers and isometries are needed to create, especially the disentanglers, to create the to remove this short-range entanglement systematically. So in our three tensor network, when we put these isometries are disentanglers, this network actually becomes a mirror. I mean, that is what we call the mirror network. So a three tensor network with isometries and disentanglers in each layer. So this is known as the mirror. So they have many interesting properties. So one can see this mirror as two ways. One is, so let's recap these things. So we know this is the isometries, which is the identity W dagger. W is identity, but this reverse is not true. On the other hand, these disentangler are just unitary matrices. So they are just U dagger and U dagger U is just the same. So identity. So these are the main ingredients of the mirror, as you see from the previous network. So we can make these isometries unitary by this way. So you know that disentanglers are unitary, but isometries are not. So we want to make these isometries unitary. So the key idea is to do by putting a product state in the two legs of this isometry, and that becomes a unitary operator. So now they satisfy this both property, like V dagger V and V dagger is an identity. Okay, so this is just a product state, which is just an unentangled state. So we'll write it just a zero state. So now all the ingredients of our tensor network are just unitary. So we can see this tensor mirror structure in two ways. One is in terms of RG flow that we have previously discussed, just systematically remove this entanglement structure, and another way is to interpret this as a circuit, and we will mostly discuss about this the second interpretation. The first interpretation is clear that we have discussed yesterday. So today we'll discuss the second interpretation. So second interpretation is just when we put all these states. This is just a mirror state with all this product state like in this way. So this is just again a mirror network. So here all this zero state. So this is we represent this as a circuit. So when we can represent this as also this way. So we just pull all the zero state in the up state. So this is a kind of circuit representation. This is our input state, where all the states are just a product state, and this is our output state where we'll going to prepare our vacuum state. I mean the ground state of the entangled ground state. So this is the representation of this represents a circuit. So this time flows. This direction means this is your input and this is your output. So this becomes a circuit. So one of the important thing in the mirror is the causal cone, where what that means is that suppose you start from this point. So the causal is a single side is set of tensors which affect this side. So this is a tensor these tensors are affecting this tensor. So if you go to the past, so you count how many tensors are affecting this side. So in this way you can calculate this, how many tensor are going to affect this state. So here you see, if you start from this side, this tensor is affecting this state, and from this tensor get affected by these two, and again this two, and again this one, and again this two. So you see this, the number is limited to 2. From first layer is just 1, second is 2, third is 1, fourth is 2, and then again 1 and then 2. So this, in this way, this causal cone is bounded, is not going to unbounded. So at each corresponding step, this descending layers broaden the causal cone. As you can see, this descending layers just broaden the causal cone because the descending link process mix neighboring states, the isometry squeezes it. So we need this causal cone is bounded. This is a very important property for the computational efficiency. For in the theoretical case, you may not, it may not be clear that why this is required, but for numerical efficiency, this boundedness is needed. So whatever meta we'll talk about has this bounded causal. So this is what I need to say about meta. So there is another point. This is which is connect meta as a holography. So Schwingel argued in his paper that meta is a discretized version of the ADS spacetime, which is known as the ADS meta correspondence. So these things come. There's some questions.
Yeah, I have one question. Yes. Yeah, sorry, I missed your lecture yesterday, so I should say that. But about this causal cone that you drew, so if I see that the causal cones of other site, if I start from, let's say, 5th site from here, which you have already drawn, then the causal cone will, after 2, 3, maybe 2 steps, it will interact with the causal cone of the first one. So do you have to, so does it affect your computation somewhere? You have to take care of that. And what are you trying to say through this causal cone that I missed?
Yes. So if you start from also this state, there in some point this causal cone gets affected. So that has been taken into the consideration when you do these things in numerical things. For example, if you calculate some density matrices, some operators, so you plug this some operators here and here. So I mean, in the numerical calculation, you have to consider these things, and this whatever you do even in that side, your causal cone should have to be bounded this way. So this property is just a property of this network. Your causal cone has to be bounded. It's not like for a particular site, right? So you can have. Yes.
And what are you trying to say through this causal cone? Can you repeat once more, please? Other than the boundedness of this causal cone, what are we learning from here?
So the thing that we're going to consider, this causal cone will not affect it in our calculation, but for numerical efficiency, this causal cone is very important thing. So whatever meta structure, when we talk about any meta, any structure, we will assume this satisfies this has a bounded causal. So unbounded causal cone doesn't have a numerical efficiency, so we'll reject those network if we have such network.
Okay, but won't it always be bounded from the construction?
This case, yes. This is a ternary network, so this is basically 3 sites as getting 1 site. There are some network structure you can put, for example, 5 sites is 1, and then again 2 sites. So some structure doesn't have this causal boundaries of this causal cone. So for the discussion we are going for the binary network or ternary network, this structure is inbuilt in this case. Yes.
Okay. Yeah, thank you.
So as I've said this, for the theoretical perspective, when you will going to compute these things in the next part of the slides, these causal things will not come across. But when you can do the numerical efficiency for calculation of observables in this method, for example, 2D in simulate the 2D Ising models and calculate some operators. So we need this boundedness of causal cone. So this is an important property of meta. That's Okay. So this ADS meta correspondence is given by Brand-Schwingel in 2012, which is very famous paper. When you correspond something like, let's say, to draw something like this. So this is a meta structure. So I'll just draw something. So what he showed is that suppose you want to calculate the entanglement entropy, suppose for some side up to some side. Okay. So you want to define a region A here, and you want to calculate the entanglement entropy of this region to this. So what you do is you make some surface here, and you calculate how many legs actually are intersecting this surface. So you in the one dimensional, this is a one dimensional meta. This is a 1D meta because splitting this 1D case. So in this case, this entanglement entropy is bounded by it's not 3 side, where L is the length of this. So this is the one dimensional entanglement entropy that we get from the CFT calculation. So when you say this entanglement entropy satisfies the area law violates in one dimensional, then that is what known as this area law. And this is a similar picture if you take this as this surface as a Lewis-Tanaka surface. So you want to minimize this surface so that the minimize the number of bonds that are intersecting. So you have some question?
Yeah, so I just wanted to know, like, what is the input for this circuit? Is the input the ground state, and if so, like, what is the output? Like, what are we trying to?
So what I am doing is that this ADS meta correspondence. I want to just give a rough idea what is this ADS meta correspondence.
Yeah,
so
yes. To understand this, like, I just wanted to understand, like, this something I missed from the last lecture as well. Like, what is the input state? Is it like do you know the input state or?
Yes, input state is the product state. So in the next picture, how to go to the next picture?
But if your input state is the product state, then why did you need disentanglers?
Okay, so in the last day we have gone from this way to this way, right? So now we are interpreting a meta in the reverse direction. That is what is known as meta.
I see.
So you start from this state. So so suppose you start from this state. This is your given input state. These are all the unentangled state.
I see.
So there is some circuit and you are getting some your target state.
Okay. I see. So these ancillary zeros that you added, they are your input state now.
Yes.
Okay. Thanks. Yeah.
So this is your one dimensional. You think what you get in your product state, in your ground state. But so Schwingel actually argued that this two dimensional thing is look like a discrete version of ADS spacetime, this meta structure. So this is a kind. So he has given some arguments, and this is not clear. This is whether should be like a meta or something, but roughly this looks like a meta. So lots of things. So how can I erase these things? Okay. So So this is known as some ADS meta correspondence. So then some similar something like continuous version of meta CMeta has also been developed. So where you have a continuous cases, continuous version of meta. But here is some difference where in the meta you have a inbuilt cutoff where it's lattice spacing, but in CMeta you don't have such. So you need to put the cutoff by hand. So that's what we do in continuum field theory. So that's the only difference for the meta and CMeta. And some bulk physics has also been studied from CMeta, from bulk metric, from the CMeta construction. One can also study calculate some bulk metric. So this is done by Takayanagi, and the recent version of this CMeta, the Myers have argued, the Jefferson Myers papers have argued that this holography, so CMeta circuit might be the optimal circuit. So you see, when we talk about the complexity, we have a products, we have a input state and we have an output state, reference state and a target state. So there is some circuit that takes us from reference to target state. So Myers argued that the optimum circuit that takes from this space to this space is should be like a CMeta circuit. So till now there is no argument why that should be the CMeta circuit, but in the path integral optimization that I am going to talk about, we'll see that something similar structure suggesting that this meta structure is the optimal network. So still any questions? Okay.
So what do you mean by CMeta circuit as complexity?
CMeta circuit.
I didn't understand what do you mean by the last point.
Okay, so forget about the CMeta. Suppose take this this is meta. So this is your reference set, and this is your target state. Okay, so there is some unitary matrices, some unitary gates, some sequence of unitary gates which takes you from reference state to target state. That is known as the complexity, number of gates, the minimum number of gates. So Myers have argued that this you have some kind of structure in your circuit. So Myers have argued that your structure might resemble this meta, preferably this CMeta, because they are constructed in continuum cases. Because CMeta is just a continuum version of meta.
So is the statement that there is a unique meta circuit which some algorithm to construct the circuit which will take from product state to any target state? Did you mean? Is that right?
By this statement, I'm meaning that you are given a reference state and you are producing your target state. So there are some sequence of unitary gates. For example, so this is your target state. This is your reference state. And this is your target state.
Oh, okay.
So this is just all the unitary operators you need. It's a sequence of gates.
Okay. So did you not explain what is the algorithm to construct this circuit? I'm slightly lost. Was there a unique meta circuit given these two things, like psi t and psi r?
No, the Myers didn't say that this has to be the optimum circuit, but it resembles whatever optimum circuit will be. It looks like a meta, and that will be a unique circuit. Yes.
Yeah. When you say meta, I mean I'm kind of confused whether there's what do you exactly mean by meta? Like
meta means this circuit is full of entangles and design in some sequence.
So there's an algorithm to construct it. Like, would I be able to construct given a target state?
Okay. So I have to say this thing. So you start from your reference state. In the next step, you put some isometries, and then this disentanglers is now your entanglers, which creates entanglement because you don't have entanglement in this structure. So in this way, you have seen this is a disentanglers, but when we talk about from this way, we say this is an entangler. So this entangler actually creates entanglement between your states. In the next step, again, this isometry and this entangler again creates entanglement in this state. So whatever your final state is a highly entangled state.
Okay. maybe can I ask something slightly different from what you're talking about? In ADS, is there a sense in which if I take an analysis of width of radius, like as I go towards the boundary, the state in the field in the annulus gets more and more entangled?
Yes, yes. This is your boundary field or CFT field, CFT, and this is full is in your bulk.
So so the statement is true in ADS also. If I take a region towards the bulk, it's lesser and less entangled.
In your bulk is less and less entangled. Yes, yes.
Okay.
Yes.
Okay. Thank you.
Yes. But Schwingel argued that this structure has an ADS Mera correspondence, but it's not clear this is ADS because some people argued this Mera has also a structure like de Sitter spaces also. So this issue is not clear, but this Schwingel also argued that whatever the structure, it has to be some hyperbolic structure, this Mera structure. So Myers have stated whatever. So this is by the statement that it didn't prove anything, but they have argued something. So your Chimera circuit might be the most optimal circuit. So in the path integral optimization in the next slides, we'll see from the different point of view that you will get the Mera circuit as from Tensor network, and this also suggests that your circuit as a Mera circuit is the optimal circuit.
Karan, go ahead.
Yeah, I have 4 questions. I mean, do you want me to ask it now or should I ask it later? I mean, based on time, Parthiv. I mean, if you're running out of time, I'll ask it later.
No, okay, just you can ask.
Okay, so question 1, I mean, is the most pressing. What do you mean by optimal? What is your protocol for defining optimal right now?
For optimal means you have a minimum number of gates from going from reference state to target state.
Yeah, so how are you measuring that?
Yes, there are issues. So what Aranav said that you find some geodesic from a different manifold and you calculate the length of the geodesics. In the next section, from when you take this correspondence from we'll see this is given by some action by minimizing some action. So this is a number of gates. So
okay, so from the action perspective, you will give a definition, but right now you're leaving it a little ambiguous. So question 2 is in this ADS Mira, you're talking about some ADS CFT sort of thing. So there must be some scale invariance involved in this tensor network.
This is
so
a scale.
Where is the scale invariance?
This is a scale invariant Mira. Suppose I mean this goes to this is a scale invariant means because you in this case you do not see the scale invariance things, but when in a if you imagine a continuum version of these things, this is actually a scale invariant Mira.
So how does that show up? So the operators are the same. You have got unitary and entanglers.
Yes,
so,
yes.
How does the unitary and entangler manifest as scale invariance in the CMERA network?
So in the CMERA network,
just on the basis of these two operators, unitaries and entanglers, how are you saying that there is scale invariance? Is this put in by hand or is this something you derive?
No, we do not put it by hand. It is something is inbuilt.
So how is that?
So in the CMERA construction that these disentanglers have some. So this network has some exponential of some operator, right? Some exponential of some operator.
Question 3 is okay. I'll ask the rest later. I mean, I think you.
Yeah. And another thing that I would like to mention is the definition of complexity in the field theory is still unknown, is still ambiguous, is not known. I have given, I will give a definition in terms of action, but it's still unknown.
Okay, I'll ask later. Okay, thanks.
Lata, go ahead.
Yeah, I have a quick question. That you said you start from a product state, and then by doing this circuit, you go to a ground state, entangled ground state. So is there a step where you variationally optimize to ensure you are in a ground state, or how do you ensure the ground state?
Yes. So these bonds have a dimension. So this is like a tensor. So in the first lecture we have seen there is some bond dimension. This is chi. So we have to variationally optimize this bond dimension, which gives us a least cost when we get the ground state. So our variational parameters are the bond dimension of these entanglers and disentanglers. So we have to minimize cost with respect to this in numerically. So analytically, this is not.
Okay, but I thought that cost minimization is about the circuit that you want to use and the unitaries that you want to use. There should be another cost for ground state, no?
So if you start from this product state and you apply these disentanglers and isometric state, so they have some bond dimensions, right? This connection, and you get some state. So this may not be your target state what you are aiming for. So you did the variational optimization in the quantum mechanics that we have defined the variation a answer. That's why this name is the ansatz. So you make an ansatz and you variationally optimize these parameters. So what is in this bond dimension, and whatever you get, you demand this is our product state. At best, this is our product state. I mean the target state. It may not be the actual target state also, but you demand this is a target state. I mean, we start from an answer that this is our target state. We then variation optimize the things.
Okay, maybe we can discuss over Slack.
Okay. So the next thing is the tensor denomination group. So for this we need this important thing, this singular decomposition. It means that suppose some given matrix M, some M cross N matrix, we can decompose it in three matrices. This is some unitary matrices, and one is it's not a diagonal matrix, but which have only diagonal elements, and these diagonal elements are known as the singular values, and we can arrange this in some descending order. So suppose the first element is bigger, then this gets smaller. So one thing is mentioned as this singular decomposition is not unique. So but when you decompose it in this way, this single SVD is unique. So we need this singular decomposition in the following section. So partition. So next we can write any partition function in terms of tensor networks. You see, suppose for a 2D statistical system, this is a partition function. So the Hamiltonian is given by something like Ising Hamiltonian, and if we define like tensors like in this form, so we can write the partition functions as a product of this form. So this tensor is written as a tensor network. So all the tensor network and all the indices are contracted. So from this step to this step, this is if it looks like a very simple step, that is just next step, but it involves some other steps. For example, Suzuki-Totaro algorithm. So we don't need to bother them. Just we want to and to emphasize that there are if your partition functions can be written in terms of tensor networks, and tensor networks are given by like these networks. So every spaces and fields they are contracted. So similarly for path integral, you can also write it like a tensor network of trace, where the tensor trace is that we have previously talked about this tensor trace. All the traces the indices are contracted. So the thing is that your partition functions or path integrals can be represented in terms of tensor networks. So the step is not very simple, but it's ultimately it's like looks like this. So any question? Okay. So tensor, the program of TRG is basically you have given a tensor network, you define another tensor network such that your tensor trace can be approximated like this. So your partition function is given by this tensor trace. So your partition function is approximate. More or less remains invariant. So there are two catches how these approximation symbols are doing. There are some errors you need to calculate and you need to minimize these things, but we don't need to bother in our cases. So then the thing is that given a tensor network, you can define another tensor so that your partition functions can be written in terms of invariant. So in this way, you can squeeze your tensor networks from T to T prime and again a T double prime. So I'll talk about what this D means actually. So you can get a smaller tensor network in this way. Okay, so this is how the TRG algorithm works. Suppose this is your tensor, the 4-rank tensor. You can do the singular value decomposition. So this is your singular value decomposition. You define a S1 and S2, and there is a matrix which diagonal elements of this S. So your D square values, so because you are just squeezing U and L together and R and D. So this is your one matrix, second matrix. This is the singular values. You can also do it this way, as this has been shown, and you can. So the tensor network, what is given your tensor network, this network, 4 network, you can just contracting each side this way. Okay, so that this gives your network T prime. But there is a problem. So problem is that if you keep all the D square values, so in U and L, all are runs from a D value. D is your bond dimension. Okay, this is a bond dimension, so all runs from D values. This is also D values, so this is a D square values. But the tensor network TRG algorithm is that you're not supposed to sum over all the D square values, but just keep some D cut values. D cut value is the largest singular values. So largest singular values means this is your singular value decomposition. So you keep some up to some values and you reject all other values. That will give you some error that you have to take count of. But suppose you keep up to some value, some lambda up to some lambda 4, lambda 5, and you do these things. Instead of D square, you go D cut and do the same thing. So that will cost you something and will give a coarser network. So what you get is just something like similar things. So all the networks are contracted, and in the next step, you just do the contraction. This doesn't cause any error. This is just a contraction matrix summation. So you get a coarser network. So in this way, you can start from a large lattice structure and get a coarser network. This is the program of a tensor information group. So any question? Yes.
I think can you go back another? Okay. So this slide, what is happening in the first case? You have T, then you are blowing it up, right? So this vertex, T vertex is basically divided in 4 parts, right? This red, blue, this 4 parts. And now what you are doing is you are putting a cutoff. This lambda 1 to lambda r, that whatever you have. Then since you have arranged it in descending order, you put a manual cutoff. Cut it off, then this T prime is your after cutoff thing, right? This,
yes.
So this DLA, okay. So T prime is after cutoff. Okay. And now go to the next slide. So next slide, you are doing for each T, each position, yes. You are doing the same thing, right?
Same thing, yes.
Right. Okay. So for each T, you are doing the same thing. Then whatever you are getting is this again T prime. So in this way, number of vertexes or whatever number of vertices are same, right? From A to C.
A to number of
vertices. I mean, go back one slide. Probably a trivial question. So first slide you have one vertex, and after doing all this thing, you still have one vertex, right? T and T prime.
No, because this this to have this, you need another tensor, right? From this.
Oh, okay. So these are not. I was under the impression that T is you are breaking this vertex in these 4 points. Is it?
Yes. So this can be represented in this way or this way. So in the top network, you represent from this way, and the bottom things you represent in that way.
Right. Then
you just contract each of them this way. 4 tensor into 1, just a contraction. So you get a larger network. So that's what
Right,
it is.
right.
If you have a similar vertex that doesn't.
Okay, understood. Okay. And but I have to now I have to make sure that I have to keep my that cutoff in my mind, right? And
Yes,
cutoff is now it's a value.
now this index answers the decut, not this.
Right. Okay.
So the cutoff decut has to be the most decut can be d square. So if you keep decut as a d square, so you didn't gain any numerical advantage. But if you keep decut as less than d square, then you get a numerical advantage. So the thing is that you at best you can try this decut as equal to d. In this way, you can change in each step. You are doing this thing, so you get a coarser network. So yes.
What do the colors stand for?
Colors are just to understand this thing. I mean, it's nothing. If I can write this same color, this may be confusing. So I'm just for green, you are dividing this way. For example, this way, right? Blue and yellow, and if you divide the valve as purple as black and red. So this is just this doesn't in a different. This all that is the same. Just for understand.
So should I understand some tensor network which looks like the middle one, which looks more detailed, is actually a simple tensor network like the square lattice you have on either ends?
This network as in this.
I'm just asking somehow the middle picture looks more complicated to me, and then you're saying it's equivalent to.
This is not equivalent to this one because you have keep a decut, so there is some error. Okay, so if you keep a d square cutoff, so if you keep it like d square, this is equal symbol, but this is not equal. So you keep the largest cutoff, so it's a decut. Okay, so you go from this way. You have some error. You have to take care of in numerical calculations. But for our case, you don't need to bother this. But and from this, this is just a indices contraction. This is just indices contraction, summation of indices. There's no error in this process.
Also, I should contract the same color indices. Is that how it is?
You have to contract
the same color.
No. This just for reference. I mean, you are doing.
Okay.
This is just a contraction. The tensor contraction that we have previously talked about, just a summation.
Okay, thanks.
So colors are just arbitrary.
Karan, go ahead.
Yeah, what's concerning me is how you're doing the sum. So if you go to the previous slide, you're summing over two S's and you're saying take the maximum value basically and then proceed. Now, if I consider the sums in some other way, some other ordering, and then I proceed, my T prime is not uniquely determined by T by your prescription. Is this correct or
wrong? So this is just the singular value decomposition. You define a tensor in terms of three matrices. So you can, so in this way, you can do it either way. So just into this two fashion. Okay.
Right.
So what in the other way you can do it?
But yeah, so you've broken it down and you're taking the sums over different S's, but this decut is defined independent of the pairs of S's, or they are defined for every pair of S's?
This is defined
for every pair or just for the entire set of 4 points? I mean,
no, from the first step. This is your first step. This is your one step. For example, take your first step. So first step, your decut is something so you get a network. In the next step, when you do again this SVD and this, your decut may be different.
So it's done 2 points at a time, sir?
Yes. So in the numerical, you define in the each step you are calculating. If you keep some errors fixed, so you decut also going to decrease in that way.
Okay. So basically, then the final T prime could be, there are many different possible T primes, and you'll find the most optimal one and choose that. Is that what you're saying?
Yes. In the numerical, yes.
Okay. Yeah. Thank you.
So any other questions? Okay. So the point is that this is the first approach when this RG techniques has been implemented in calculating the partition functions, and is very successful in coarse graining techniques. So off criticality is very, very vital, but this doesn't filter out the short distance fluctuations as also taken, because this sites are entangled, some more entanglement in some sites. So these are doesn't distinguish which sites are entangled because they do not filter out the certain fluctuations. So the fixed point tensor we get from this, they will contain the certain information, as this is similar as the T-tensor enumeration that we have talked about. So these tensor networks, this TRG program breaks down at critical point. So we need to figure this out. We need to figure this out, how to eliminate this short range distance fluctuation that we have previously encountered. So this program is done in the tensor network enumeration approach. So TRG approach is basically, the goal is to remove this short range entanglement, and for that you need to use disentangler that we already know. So there is a complicated thing that when you use the disentanglers. So okay, so the main thing, you start from a coarser network and you want to reach from a coarser network. You want to start from a denser network and you want to reach a coarser network. So here are the steps that you have to do to reach it. So in this step, you incorporate some disentanglers. So the step is this slides. So this is your first A. So what is given this? So take for 4 sides. This is your A. So in this step you add disentanglers and isometries. Okay. So here are some complicated methods, but for simplicity, let us take, this is your disentanglers and this is isometry, and you make these disentanglers into a new tensor B, when your B tensor is defined like this way. So this is your B tensor. So you added a B tensor. So you get from this network to this network. So what you get from this and this. The next step, this is your U and this is the U dagger. So they annihilate and you get a different network. And the next step, you select, you define, you break down your B into some other tensors y prime, such that this y prime, B and X are this identity. So you get a B tensor in this tensor. So you can write this your B as a defined in this cube, blue and red and blue. So red and blue. So in the next step, you have this network structure, red, blue, and this. So you add some projector that will introduce some errors also. In every step, you have some error that you have to take in numerically in each step. So that you have some projector, and you can take this as a whole A, and you write as some A prime. So you get something, and you have omega dagger omega is your isometric annihilate, and you get it. So there are lots of steps are involved in between in this network, but the ultimate thing is that when you go from this denser network to a coarser network, your short range entanglements are removed, and at least you want to try to remove something, some short range entanglement removed. So you again apply the same process again and again. So all these steps are done numerically. So this is your tensor network algorithm. So you use the disentanglers in your each step to coarse grain things. So any question? Okay. So this is your TNR program. So now you do the TNR things in one is an open boundary. So this open boundary is needed when you prepare a state in the path integral approach.
Pratik, yes. Can you just go back one slide? Okay. So when you are going from A to F, the question that Karan was also asking. So is there, since these are like, I mean, okay, renormalization group and all that. So is the scale invariance related to this part? I mean, some sense. The scale invariance he was asking.
The scale invariance, which scale invariance?
I mean, the scale invariance that Karan was asking, no? So because if they are talking about ADS,
okay. So this is a so now we have don't talk about any ADS. So this is a different perspective, right? So we just write our partition functions or in terms of these networks. So we do the coarse graining. So there is till this point there is no ADS at least, but we'll come across this ADS later.
Okay.
It's just some something like your partition functions or this thing. You just breaking tensor networks things. Just no ADS as well. Okay. So any other question?
But is that cut prescription to calculate entropy still valid? Cutting prescription, RT like prescription you mentioned.
Cutting this. Okay. So if I'm not sure. I've not seen people. I'm not seeing any paper that talk about entropies as yet. They calculate the entropies for the MERA, but in the TNR things. So basically, we'll reproduce MERA structure in the from the TNR structure. Then this entropy thing will be valid. But from these things, I'm not sure. I don't. I think it's valid, but I'm not sure. So the next step you see the TNR actually yields the MERA. So when there is an open boundary condition, when we talk about the state preparation from path integral approach, so there is an open boundary, which means there is no tensor in below this half plane. So we do the tensor network TNR algorithm things. So this means that in the boundary we are actually producing this entanglers or disentanglers, because from here if you see these things, so there is this W and this U, there is no tensors in the lower half plane that will cancel these things, so that will remain. So again, if we do the tensor network thing, these entanglers and disentanglers are actually keeps on increasing. So finally what we get is like a MERA structure. So now as Akhil was asking that if tensor networks this area calculation is valid, now it's valid in this structure. So actually, so what that means, if you have some open boundary condition and you do the tensor TNR algorithm, you'll precisely get the MERA structure. So this is done by even Leon Wiesels in the paper. So this is for one open boundary condition. Now this is if you have a two open boundary condition. For this is for example, this is a thermal MERA. So there is a length beta, and you do the same thing TNR thing in the two sides. Now what you get ultimately is a MERA structure in two directions. So the Giedel and even they argued that the connection, that a single layer connection that given by the Courser lattice is actually the Einstein-Rosen bridge from if you think this is basically a two-sided CFT and this is a MERA, so something like this. So this issue is not very clear whether you can actually write this from Rosen bridge, but Myers and other people have argued that in the complexity calculation, if you take this as a Einstein-Rosen bridge kind of things, you can actually reproduce what in the without doing the tensor network. So this is just a justification.
So yes. would this give a very concrete check for this complexity volume? Or
yes. So the thing is that the tensor network is not the direct way to compute the complexity, but that will give a check that whether you are getting things are correct or not.
So what does this say? Does it say area or volume?
Sorry?
Does this kind of analysis imply area law or volume for the?
Yes, this implies the area law, because this is just a MERA. Like this is a MERA. So MERA always implies the area law by the construction.
Okay. No, I meant for the complexity, not for the.
Oh, complexity. Complexity means this complexity action.
I thought you were interpreting this as the optimal circuits, right?
Mm-hmm.
And then you have you're saying there's some kind of ER also. So actually I'm not exactly following what you're saying, but I'm just trying to.
So this is your. These are your. Yes.
Yeah. So I'm saying since you mentioned this course coast lattice in between is like a Rosen bridge or whatever. Is there a sense in which you can? I'm just wondering if you can at all pose this question. Like, I want to. What is this kind of tensor network studies like indicate about the complexity equal to volume or complexity equal to area conjectures?
Yes, this. So this is your two-sided CFT, right? If you take this to open boundary to states, is a thermal mirror. So this is, so if you do the tensor networks these tensor network things, so this is, so in the Schwingel's paper there is it doesn't have this middle line because it doesn't apply this TNR algorithm, but the TNR algorithm actually produces a single layer which doesn't contract it. So this is a kind of one layer which actually bridges between these two sides. So in this way, they have argued this in the field theory description, they can be interpreted as the Einstein-Rosen bridge from two sides. But still now we don't have any complexity. We just do the tensor networks things. We don't talk about any complexity. I have told that this might be optimal circuit, but I didn't give any argument why this should be the optimal. But some circuit, but may not be the optimal, may not be the complexity, whatever. But the complexity calculation, what Myers did, they argued that the calculation, you do the complexity calculation as volume and action calculation, and you do the TFD calculation. For example, this complexity of formation. So this means that suppose you have a TFD state in terms of two CFT state, you want to calculate the complexity of the TFD state and the two CFT state. What is the difference between these two things? So for example, if you like this complexity of TFD state minus the complexity of two CFT separately, two CFT states separately. So what is the difference between these states? So they have calculated using the action complexity equal to action calculation, and they got some result. So now they are pictorially thinking this is a TFD state, and you have the two separate CFT state in our previous slide when we have just one open boundary condition. So now you subtract from this TFD state and this one CFT, this two CFT state, two CFT. So what you get, you can argue in this language that this is same what you get from CA conjecture. Is the same. The coefficients of before in the previous doesn't match, but the divergence or whatever in the main property of the CA structure actually valid in this calculation.
Karan, go ahead. Karan?
Yeah, I just want a clarification on one point. So each of these diagrams you're drawing and you're saying it's time, it's basically the holographic direction. Is that correct? It's at a fixed time and it's holographic direction. Is this correct?
It's a fixed time and the holographic direction. Yes.
Okay, so this diagram you've drawn from A to C, this is a little left field, I guess, but is that a transition from a vacuum state to a black hole state? And if so, is your RG flow capturing like a Hawking page transition as well?
No.
Why not?
No.
If not,
No.
Why not?
So
in A, you've got no black hole.
Sorry.
You've got no wormhole. And when you go from A to C, you end up with this thermophile double state. That's literally what you wrote, right? C thermophile double minus C of two CFTs is equal to something.
Yes.
So this is a Hawking page transition, right? From the vacuum state to the black hole state.
Okay. Yes.
So I don't see the connection to complexity just yet, because complexity action would require you to take time as well. So you'll have to do the tensor network in this Wheeler-DeWitt patch, if I'm not mistaken. Yeah. And then that Wheeler-DeWitt patch would scale with the volume as well. So there'd be an extra dimension to what you're drawing. So like this is a fixed time, but that would have to perhaps go into, that would have to go in the time direction as well. Is that correct or not? Or you would be measuring the number of gates that are increasing with each time step, right? Time would have to enter into your complexity assessment. It's always DC dt is less than something in both volume conjectures and action conjectures. So you cannot make a statement on complexity without taking time into account. Is this correct?
Yes. So isn't that this the beta that we are talking about?
Yes.
So this is basically that inverse of the temperature. So
right.
So this is when you talk about in the pathological representation of the density matrices.
Yes.
Okay. So this beta is just isn't this the time direction?
Well, no. In some sense, yes, it's a Euclidean time direction, but it's not a time direction. It's not a time direction in the sense of what you would be doing in your two-sided black hole picture. This is just beta fixed for the to give you the temperature at which these two matrices on either side are in equilibrium. That's very different than the HL plus HR which Orpita was talking about.
Oh, okay. So I'm not going to talk about this HL. So all the things I'm doing going this Euclidean things. So whatever path integral you are doing this Euclidean path integral. So I'm just making a connection. This, for example, if you talk about an open boundary conditions, you get a mirror, precisely mirror structure, and the open boundary condition you prepare a state. And if you have a two open boundary condition, you prepare a density matrices, right? So, for example, then you can get a two mirror in two different directions and a tensor network which is not contracted, but it still remains. So this tensor network is a some way is connecting between the two states. So in the sense that this might be a connection of this TFD step. That's what I mean.
Okay, and just to be clear, we are saying nobody has so far connected this flow that you've shown from A to C to some kind of hopping page transition just yet.
No, I have not seen anything.
Okay, thank you.
So these are given by this event will be there paper, and this complexity in this Myers and they have talked about formation of complexity. They have calculated this in the CA conjecture, and they have matched this result using this tensor network. Just giving some argument to this tensor network diagram. So tensor network just basically is some kind of checking that your calculation is whatever you get from C and CV is valid or not. So in the similar cases in the path integral derivation we also give a tensor network argument to get the Liouville action, the path integral complexity that we will be doing. So these are the two websites that I think many will get interested. So if you want to if you are interested doing the numerical things in this tensor networks from the MEDA, so you can visit these two sites, especially the first one. So they have all the ready-made programs and everything there. They have tutorials, everything. So you can
Pratik,
go ahead. Yes.
I want to ask something really stupid, but like you showed this picture where you had two boundaries and then you were saying that constructs a density matrix, is it?
Yes.
So I'm just wondering, like, though I don't understand what we are doing exactly, but like, why stop at two boundaries? I could add multiple boundaries, is it?
You could have multiple boundaries. So this
because
is
it's
your
just
two-dimensional. This is a two-dimensional thing.
I mean, it's just a spatial slice, right? There's no time in this A picture. Is that right?
Yes. Just you can have this bounded this way. So
I'm just asking, sir. I could have a tensor network with four boundaries at the least, no? In the picture you are showing. I mean, as in cut the periodicity condition in the direction you have left without any boundaries added, and like add more. Does that make sense? Like to add more boundaries.
So I am going to prepare a density matrices. So to prepare a density matrix, you need to give two boundary conditions, right? In the
Yeah, but it seems in this A picture I can give 4 boundary conditions, no?
From here and here.
Yeah, maybe I'm not understanding.
This is just extending this way.
Yeah, I thought it's periodic. That's periodic, no?
Yeah, periodic, of course, yes.
But I could cut and give 2 separate boundary conditions.
And yes, you can, but will that prepare a density matrix or something?
Because I thought the time direction will, it's not, none of these are time directions, right?
No, this is not the time, it's a special direction.
Yeah, so then I could have different boundary conditions, no? What do I land with? I land with something with four states.
Okay, so this is your time direction actually. So
in
your time direction, this is your time direction. So this is your special direction. Physics.
Okay.
Can I ask for a short clarification?
Yeah,
I mean that is your Euclidean time direction, right? I mean, so what Akhil was asking was in some sense correct. You could always take another kind of periodic direction in the x direction, and that would presumably give you some kind of torus kind of partition function or something like that. It's a perfectly legitimate construction. You can take 2 sets of boundaries up and down and 2 sets of boundaries left and right.
Yes.
I mean, what is wrong with that?
No, it's not wrong because in this paper actually they have considered this boundary condition is a torus-like structure, but to get a proper density matrices, you just suppose you take some cutoff, some L in some boundary condition, right? Some to put some L length. So you get a density matrices when L tends to infinity in their construction. So clear or something like that. Suppose this is your length L. So you create a density matrices rho L. So now you take a limit L tends to infinity. So and that will give you the matrices that you want to construct. You can put a boundary.
Okay. So this diagram you have already includes time, but Euclidean time. Is that what
yes, Euclidean time.
Euclidean time. Then I'm fine. Thank you.
So next we talk about this path integral complexity. Right? So it's a different kind of complexity that we have came across. This is based on the Euclidean path integral. So this basically optimization procedure to prepare a CFT ground state in wave function in arbitrary dimensions. But we will mostly confine in 2 dimensions. But let's start with the arbitrary dimensions. So the optimization means the minimization of certain functional with respect to background wave. So this 2F in the 2D CFT, this function is allowed Liouville action that we'll see. So in the path integral approach, how do we prepare a ground state of a function? So we do a path integral over some background metric, right? G, and it's a Euclidean action, and the fields are defined as so that this is the Euclidean time. So minus of Euclidean time basically. So runs from epsilon to infinity. So and this is where you prepare your ground state. This is a boundary conditions where you prepare your ground state with respect to this background. So, and usually this background metric is taken as a flat. This is the definition of the ground state in path integral. So in the tensor network picture, you represent the path integral in terms of tensor networks, and the optimized network by choosing various parameters of particle network. That will how you do the tensor network thing. So here the parameters. So then if we represent this ground state wave functional in terms of tensor networks, so what will be the parameters of our tensor network? So the natural candidate is the background metric G that we are going to equal this path integral. So the question, so one question you can ask, if we evaluate the path integral in a different background metric, instead of G hat, we define a different metric background with the same boundary condition. So can we choose this new metric optimally such that it produces the same ground state after some normalization with the same boundary condition? The boundary condition is the same. So the question is yes. So if you start from a 2D matrix, so here the comes as 2D, we'll discuss only about 2D. So for the 2D case, we take our flat metric as this 1 by epsilon square and dz square. So and the metric we'll choose is some e to the power 25, because any metric in 2 dimensions we can write in just a conformal factor times this flat space. So in the boundary condition that we previously talked about is just given by 1 over epsilon square. So 1 over epsilon square. So mathematically, what this means that if you change this metric, so this is your metric, and your metric is just to the power 25. So if you change it e to the power 25 to g, then the new wave function will take some exponential factor which is dependent only on g and the field phi that we are going to talk about. So this phi is just this phi. So the definition of path integral complexity, this is just a definition. The definition is the minimal of this complexity function. This complexity function for some particular solution, phi equal to phi 0, which you get a series of this functional. You take a minimum of this phi and you choose this phi. Evaluate this phi at some phi 0, and the definition of complexity is just the optimal function of this phi 0. So in 2D we can explicitly identify this function as a Liouville action. So two ways we can show. One is just basically the explicit calculation and nice argument given by this check in respect from this TNR argument, and this TNR argument also only for 2D, but I will make also a comment what can be in for higher dimensional case also. So for the explicit calculation, so so when you take this e to the power 25 is because this is kind of anomaly things, it takes a exponential factor, and this factor is given by the Liouville action that we have already came across. So our aim is to derive this action somehow from some principles. So till this is clear or question? Okay. So a direct calculation can be done using this just exponential factor. And you calculate the Jacobian. You do the trace of the Jacobian, and this is some regularization method you do just as you do in calculation in the well anomalies or something in the electrodynamics or something. So you do the same things do some regularization trick in here, and you get the Liouville action. This is a non-trivial exercise, but it's not so trivial. But you can do this thing, and you can check this is given by this. It'll give this. You'll precisely get this action, this Liouville action, if you do this anomaly calculation. But we'll do it some other way. So this argument is inspired by the paper by Check. This is a TNR argument. So suppose you start from this is a tensor networks. Okay, not suppose this way. This is a tensor network. So some infinite tensor network. So you define some fields phi in your ground state. So it's something epsilon is just your lattice spacing in S equal to 0 layer. So in the S layer, the field is given by this minus of log of 2 to the power S epsilon. So now the tensor network actually tells that if you do the tensor network, you get a bigger tensor network which has a defined with the lattice spacing is just 2 to the power S plus 1. So so the thing is that how will you get from this step to this step? We know that from the TNR argument we know there are some arguments, some descent angles and isometrics will be present in this layer. But the process is that if you start from a S layer, you get a S plus 1 layer, and intermediate layer where these fields is given by this entanglers and disentanglers. Sorry, this isometries and entanglers. So from this network approach, we can calculate what is the action. So at the action, we means what is the complexity of calculating each of these tensor. So the first is the volume element. So the volume element is just a 1 over epsilon square, because your metric looks like just a 1 over epsilon square. So before the tensor network doing the TNR things, your volume element is just 1 over epsilon square. So this is your volume contribution. This is the number of tensors in your network. Now you do the rescaling. So the rescaling is just a exponential of 2 phi. So when phi was epsilon in the before you start the tensor network things, you get back these things. So after doing the TNR things, your volume contribution is this thing. This is the number of tensors in your argument, in your cost or whatever you define the complexity. So there are complexity. There are formation of layers, because you have 2 layers. So the phi changes only there when there is a layers, right? So there is some. So you have some surface contribution when there comes some layer. So this contribution when the phi changes, so this becomes only given by the del phi, and this is the isometry requires it should be del phi square, because that doesn't matter you get from this coarser lattice to denser lattice or a denser lattice to a coarser lattice. So it should be in either direction. So that's why becomes square, and this is uniformity in z and x direction, because you can this is just an infinite length. So there's some uniformity in z and x direction. So your layer contribution is just a del z square plus del x square. So if you add up, you get a something contribution from what you get the Liouville action. So in this way, you calculate the total number of tensors in your argument. Is the tensor in your network is precisely given by the Liouville action, which is the path integral complexity. So the connection is that path integral complexity actually calculates the total number of tensors in your tensor network. So is that clear?
Sorry, can you just remind me what mu is?
So mu is just a contribution from each tensor, because you just multiply some each tensor.
And what is the? I mean, does it have to be positive, negative, or is there
No, this is just positive, because you have just a contribution from tensor. I mean,
doesn't the action then look unstable? I mean, the potential in the final Liouville action that you've shown.
This one.
Yeah. So if mu is positive, isn't it unstable?
So mu is actually decaying by 1 over epsilon square, but it's not unstable because unstable in the sense.
I mean, it's not bounded from below.
Okay. Actually, yes, because actually the total numbers of, because as I've said, this SL counts the total number of gates in the tensor networks, and is actually infinity. Because you have an infinite integration, right? So it's actually infinity. So this is not bounded. So the total number of is given by the Liouville action, which is actually in principle is infinity. Total number of tensor. Yes. But you have some form. So the total number of gates or tensors. So you write now you say this the total number of tensors is actually, each tensor is like a gate. So total number of tensors is like a total number of gates. So whatever calculating we are doing, so this SL is basically a total number of tensor. So this might be a density of gates, right? This might be density of gates. We'll see in the next section. This actually is given by the density, can be given interpretation of density of gates. So this is the total number of tensor, which is in principle is infinity. Yes.
So this density of states is basically the continuous limit of whatever the gate calculation we were doing earlier in the discrete.
Yes, yes, yes. Just the density of gates. This term. Then we'll show in the next section that is indeed the density of gates. From here, you can guess this is should be the density of gates, but we'll do some other things. So, any question?
Karan, go ahead.
Yeah, I'm a little confused about something. So your entire theory is in 3D, if I'm not mistaken. Like X, there is X and Euclidean time on the boundary where you define Louisville, and then you are building this into this holographic direction Z. Is this correct or wrong?
Now we didn't talk about in holography, right? We're just doing path integral in C.
Okay, so you've got a Louisville theory. What is Z?
So this is in your field theory. So there is a field theory time and there is some special direction in 2D CFT. So we have
this is Lorentzian or this is Euclidean?
Euclidean. It's Euclidean. So Z is your Euclidean.
So where is your periodic direction? I'm a little confused.
So in principle, when you do the path integral, you take a minus infinity to prepare ground state in 0, right? So yes. if you take a tau is a minus Z is just 0 to infinity, but you start from an epsilon, just a small cutoff. And
do you have your transformation from, let's say, Lorentzian to Euclidean? Do you know the transformation in this case? Like what have you done exactly? So I started with T and X, say. So how did I go from T and X to Z and X? What's the transformation there?
T and X.
Yeah. So let's say I started with the Lorentzian theory and I went to this Euclidean thing. So what is your transformation?
I'm not sure, but so you can define your path integral in Euclidean field, right?
Yeah, that is fine. I'm just a little confused with your integrals. That's all. Maybe I'm missing something there. Okay, and the second question is, what are you defining as complexity again? So you've got this action, and then
yes.
What are you
defining? So we have defined this complexity definition. This it can be interpreted this action, right? Is I. So the next we said that this action can be given in terms of this S. So complexity is given by this S. So this is the definition of path integral complexity. So it can be distinguished from the complexity than previously we have talked about the complexity and some. So that's why this is a path integral complexity, and this calculates the total number of tensors which can be interpreted as some sense of gates in the tensor network picture. So in principle, the total number of gates should be infinite, right? So in the continuum language, so SL has to be infinity in this sense. So
no, can you go to the next slide? The next one, sorry, the one where you've written complexity is equal to I or something.
Okay,
yeah. So so shouldn't this be like I into Z or something like that? Like I mean, I thought dc dt is equal to the action divided by some factors. But you're saying here that complexity is action directly, or sorry, I'm making a mistake. I'm making a mistake. Sorry. So yeah, complexity is action. Okay. So you're just saying that this is equal to I at the minimum.
This is just a proposal, and we can check this is whether.
This is the CA proposal. This is the CA proposal. Yeah, I'm sorry. That's fine.
So for now, but there is no Wheeler-DeWitt patch and nothing. It's just for the safe thing we're doing. Right. So this is so from the tensor network argument, we can in principle derive the Liouville action and see this Liouville action is basically what you get. So the conclusion is the following. So we do the path integral calculation in preparing the ground state in this flat in this space when we have equal number of division in Z and X, right? But this prescription tells that instead of doing this path integral in this background, if we do a path integral in a different background, in different metric, which looks like a background looks like a hyperbolic slice, is a mera, will give you the optimum way to prepare the ground state. So the background matrix actually looks like a mirror that we have again we can talk about. So this is an argument again that why the background geometry has to be a slice of mirror, but still this is a hyperbolic slice. So the distinguish between distinguishing ADS and DS is still missing in this context. But the prescription is, instead of doing a path integral in original flat space, you have to do the path integral in the hyperbolic space to prepare your ground state wave function in an optimal way. So yes, so does that make sense? So this is the prescription given by Takayama and that. So from the Liouville action, we can get the equation of motion like this way, and you define some coordinate W and W bar, and for the Liouville action becomes just like a W and W bar this way, and you put the boundary condition, and you get a solution like this. So this leads to a hyperbolic matrix. So e⁻²∅ is 1 over z square. So this means that even in a boundary, your geometry is like a mirror. Till now we are not talking about any bulk or whatever we are talking about purely in the boundary. So your boundary geometry itself has a mirror structure. So in the background matrix. Okay. So on the solution we can calculate this action. So in the solution we can calculate this action, and by definition we'll get this action as on the solution is a 1 over 12 pi epsilon. So this 1 over epsilon is just a divergence we require from holographic complexity that we have shown. This CV conjecture is from the holographic complexity. But this coefficient doesn't match. So there's lots of question. I mean, which kind of complexity are going to be the actual giving you the actual value of the complexity. But naively is just the divergence actually matches. So yes. So any question?
Pratik, when you say actual value of complexity, what is this actual?
Is actual means, well, I mean, as I've said that in the field theoretic language, you do not have the correct definition of what is the complexity. In the quantum computation or in the gate language, you have the definition, the minimum number of gates. But in the field theory language, you have to define what the gates actually mean. So in the tensor network picture, we define the gates are just a number of tensors in this language. The actual complexity means there is some complexity maybe which is true. I mean, there is some definition of complexity that we do not know, but that is that I'm selling this actual complexity which is defined in the field theory language. But this pathetical complexity may not be the actual complexity. But the fact is that this has a leading divergence 1 over epsilon, which matches what is given from the holographic complexity. But we are not talking about any holography yet. So is it?
I agree that there are multiple definitions of complexity in the field theory, as we have been hearing from you also, Pita and Arun. My point is that the complexity as it stands, or if I understood correctly, it's by itself is not a physical observable at all. So it's some measure that we are free to define. We have an idea that in finite quantum systems, in quantum mechanical system, what complexity should reduce to. But in quantum, we are quite free to define modulo some consistency conditions, what complexity should be. So the way I understand it is that holographic people using holography has given some definition. You here have given a different definition using path integral.
Yes.
And the two definitions need not agree.
Yes.
but what is this actual complexity, like Platonic concept of complexity? It shouldn't be there, right? It's up to us to define. A complexity should be a diagnostic to get to some physics. If all definitions of complexity give me similar ideas or similar diagnostics of the physics question, then what actually should we, what discerns between these two notions of complexity, that this is more preferable to that? Suppose I come up with a definition. So let me put it this way. Suppose I come up with a new definition of complexity and give it to you. What should that definition satisfy to call for you to call it actual complexity as you're using the word?
So complexity. So in the sense that this somehow this complexity has to count number of gates in your theory. So then you have to define what is the number of gates, right? So here we are defining the number of gates and number of tensors. So in the sense, this action SL counts total number of tensors. So in that sense, we are defining this is the total number of is the complexity. And when you do the path integral, this measures is just if you do again this change the background again and again, this product just gets multiplied. So it's just preparing the state again and again. So in that sense, this we call is a complexity.
I think Arunno has some question or comment. Arunno, go ahead.
Yes, just a comment about what Subramanian was asking. So probably the definition of complexity that we are looking for is somewhat people are defining complexity from different perspectives in different ways, and the ideal goal would be to understand each of them in a universal setup. For example, to find relation between each of them. For example, the complexity proposal put forward by Jefferson Myers, then another proposal was put forward by Hiller and collaborators, which was called Fubini study metric. So now, very recently, there are proposals, other proposals in CFTs as well, that makes use of those Fubini study metrics as well as these Liouville actions. So all of these ideas are sort of related to each other, but what would be actually good to find out is how these different proposals are related to each other, and actually if we can find a concrete proposal for CFT that sort of matches or gets closer to the holographic proposals made, or in that way, if we get at least one of them to be related to the holographic proposals, then by the relations between all of them, we can find relations with the holographic proposal with all of them. So that would be one way to look at this whole picture of defining different ways to compute complexity in different pictures. That was all I wanted to say.
Karan, go ahead.
Yeah, just a comment. I think in some sense the broad goal is known, which is there is whatever is happening in this talk right now is to show that there is some correspondence between a way in which you talk about gates and actions. And complexity, I think, if there is a universal way in which you can talk about there being a minimal number of gates in going from some state A, which, okay, granted, you can take it to be the most trivial given state possible, just all of these zeros going to some other state, then that would be, if we can precisely state that these are the minimum number of gates needed to go from A to B, then that would be a concrete definition of complexity from the circuit side, and then its action representation or any other kind of representation should somehow make that manifest in all cases. And from the volume side, from the geometric side, I think this notion of maximal volumes are also sort of well-defined prescriptions in some sense. So I think the goal might be to sort of clarify on the field theory side, basically what it means to talk about minimum number of gates. And then if this can somehow be tied to this volume picture or corrections of the volume picture if needed, then that might be something a little more concrete as a broad goal of this program. In terms of whether or not it is a physical observable, I'm not quite sure, but it sets a bound on how you access states in the Hilbert space. I think that's the way that it should be viewed, but it's not so arbitrary, I think, as it might not just be like, okay, I say something is one thing and somebody else is saying it's something else, and both of these are equally valid. If it can be pinned down to a proper minimal gate structure, then I think we are done. Yeah, that's all I wanted to say.
So this is just a definition. So we are talking about from the field theory side, not from the holographic side. So because there is no holography yet, we just talk about anything from the field theory side. So you're just calculating the idea of total, what is the total number of gates if you can calculate some from the reference set to target state. So this is the some definition, some sense we can estimate what can be the total number of gates, but yes, this is a definition we are proposing, or we are assuming. This may not be the giving the just what.
Yeah, Parthiv, can I just ask? You mentioned that there is some way in which you can show that this is the optimal number of. This is an optimal circuit. The circuit of having entanglers and unitaries. Is there a proof of this, or is there an argument for this?
No argument. This is an argument. So as I told us, Myers have argued that this Chimera circuit can be an optimal circuit. Right. So this is in the sense that actually this thing. So they are the thing the conclusion of their paper is just that instead of doing a path integral in the flat space, you do the path integral in a hyperbolic space. So in the flat space you prepare some ground state. If you do the path integral in the optimized in the hyperbolic space, you get a ground state. So this in the optimized if you do the path integral in hyperbolic space, so that will give you the you can produce your ground state in the optimal way. That's what their conclusion. So you have to do the path integral in some hyperbolic space, and the hyperbolic space looks like in the Jensen-Letter picture, it looks like a mirror circuit. So in the sense the background geometry, so whatever we are doing the path integral is has a mirror structure, and noted this mirror is in the CFT picture, not any ADS in ADS diagram. This we have not talked any ADS. So previously I have talked this mirror network actually extend into the ADS space, but here mirror, this is mirror structure is basically in the CFT space. So does that make sense?
Yeah, it makes sense, but I was hoping for more of a gate explanation. But anyway, that is fine. Like, just at the level of gates, like ignoring any space-time, ignoring anything, that doesn't exist, is what you're saying.
So this thing is that this path integral approximation is still under a very early stage in this calculation. So people are trying to do these things, but you didn't have any. I mean, for some derivation of Liouville action from the first principle from the gravity side, that has to be Liouville action is not done yet. So this is kind of thing that we are lacking, still lacking.
Pratik, I should point out that it's already 4:02, so maybe try to wrap up.
Okay, so that is 2 or 3 minutes. Okay, so there are some properties I think is not very crucial in this sense. So I can stop. It's not very crucial.
Maybe a good idea is you can upload the slide on your slide.
Yes.
So people can read up. Okay.
So yes, that's accurate.
Okay, so please unmute yourself and thank Pratik for this nice talk. If there are any pressing questions, please go ahead. Well, if not, let me pause the recording and people can continue the discussions more informally. Okay, welcome back. The last lecture of today, Adwait is going to continue his lectures on information laws on ADS2. Over to you.
Yeah, thank you. So let me just review what we did in last lecture. I talked about entanglement entropies in 2D CFT. And I told you about how to understand the cutoffs and cutoffs, how the cutoff really enters into the formula for entanglement entropy of a single interval. Then we talked about how to calculate entanglement entropy from Rene entropies. So you compute nth Rene entropy, and then you analytically continue n to 1, and that should give you the entanglement entropy. And to compute Rene entropy, you have to use tricks like replica trick. And replica trick, I have shown, I've suggested that it's similar to just putting twist operators on a single manifold rather than constructing an n-sheeted manifold. Then I had introduced the quantum Ruth-Akanagi prescription, where you construct a surface which is homologous to your boundary region, and you vary over that surface, you extremize, and then if there are multiple extremas, then you find the minima of that, and that surface would be called a quantum extremal surface or quantum Ruth-Akanagi surface. And whatever is enclosed between the boundary region and the quantum extremal surface is called the entanglement wedge of that particular boundary region. Now, after that, I said some words about entanglement wedge reconstruction. Basically, it just says that if you want to reconstruct some operator, which is in a particular, which is in the bulk, you can only reconstruct it from a region, from the boundary, if the entanglement wedge of that boundary region includes that bulk point. And finally, within last few minutes, I had introduced JT gravity. So let's just look at JT gravity once again. JT gravity has the essential part of the JT gravity is the first two terms over here, which is the topological term and the dynamical, which I'm calling as JT. And the topological term by Bose-Garnet theorem just computes the Euler character of the manifold you're working with. So in most of the computations where I'm explaining stuff, we are just ignoring this term. It's there, but it's there, and we're just ignoring this term. Now, because you can see that as I'm going at higher and higher genus, so this chi of m, which I have written here, so this chi of m here, which is the character of the manifold, you see if G is much higher. So if you're looking at a very higher genus surface, chi m is negative, and hence this object here is negative. So it's basically in a path integral, it suppresses those contributions. So higher genus manifolds are automatically suppressed in JT gravity path integral. So let's only work with the lowest genus, where G equals to 0. So it's just that term is just a constant, which is just find out by 2G Newton. And then there is a dynamical term which has a running dilaton, or which has a dilaton which is dynamical, and it has a boundary term. And if you find equations of motion, you'll get these two equations of motion, one by varying metric and the other by varying dilaton. And dilaton gives you a condition which fixes the metric to locally ADS2 or locally negative curvature always. And then there is a variation of metric, which gives you sort of an Einstein's kind of equation, G mu nu equals to G Newton into T mu nu, and which is this equation here. So, and the T mu nu would just come from standard definition of how you find stress tensor from a matter action. So it's just a variation of that matter action with respect to the metric. And we are also considering only minimally coupled matter. Okay. So now, after this, let me just quickly go tell you how the Schwarzian description comes about in
Adwait, just to sort of clarify, so you fix the genus of your background manifold and then you go on to do it?
Yeah, in principle, if I'm doing the complete path integral, I have to sum over all genuses.
Right.
But as I showed you, when genus is higher, all higher genus contributions are suppressed by this factor of phi naught here. So there's always e to the power. So okay, let me write it down here. So if I'm
yeah, I understand the genus separation. I just wanted to, so for example, in string perturbation theory, you have this term, and this actually defines the string perturbation theory for you. So for JT gravity, do you have this perturbation theory in back of your mind? Or?
You do have, but we don't probably really have. I would only work with the lowest genus, genus zero surfaces.
Okay.
I won't consider handles, but you can consider them. Okay, I'm not sure if the story has been worked out for higher genus, but let's work with the lowest.
Yeah, sure.
So now,
so
yes.
Anderson, if you have, normally if you just integrate R on something, you will get the genus, but but once you fix it to a constant, isn't it just counting the volume of the surface?
It's not just integration of R, right? So it's the I didn't. I mean,
because I thought the phi dilaton equation motion fixes R to some constant, right?
Yeah.
And then I thought this genus contribution is just measuring. That will just be the volume of the surface, no? Then it's just R root G integral.
Well,
Anderson, R root G is like generally the Gauss term and its genus, but because fixing it to constant, I'm confused. Because for it to really measure the genus, it has to like where the surface turns in, it has to be negative, or it turns out, it has to be positive, and so on. But you also say it's constant. So what am I missing here?
Sorry, Akhil, can you please say your question a little differently? I'm not able to understand. Adwait, can you go back to the previous slide also?
I'm just writing the term again. Okay. So maybe, yeah, sure. Okay, yeah.
Okay, I'm saying suppose you do this R root G term on a torus or something. The reason it whatever the metric is, it covers, it measures the genus is at wherever the torus turns in, R is negative, and wherever it turns out, curves out, it's positive, and so on. And at the end, it ends up calculating the genus. But we also are doing on a submanifold of all the field configurations, such that R is a constant. So then if you put that in, and if you once you substitute that, the R root G term is just calculating the volume of the surface. So I'm slightly confused. How does it reconcile with?
Sorry, how does R root G computes volume?
Because R is a constant, and then root G is just volume.
But that's after you do the path integral, right?
Yeah. So I'm just asking where is that's okay, but then I'm just confused. How does it really count the genus?
Yeah, I mean, you have to look into the proof of Gauss-Bonnet theorem. I really don't know. I mean, it's just the statement which is written here, like left hand side equals to like this equality is just Gauss-Bonnet theorem. So I understand what you're saying, and but I can't think of it right now live. So
only way I can think of it is that it somehow this lands you uniquely on the trivial genus surfaces or something.
No, it doesn't land you on trivial genus surfaces. You can work with any genus.
Okay.
It's just that if you do this particular integral on that genus, on that manifold in 2 dimension, if it's a 2D surface, and if you do this particular, and okay, it has to be a bordered surface. So there's specifically an existence of a boundary manifold. If there's a boundary manifold, and if you do this integral, you'll get the genus of this surface.
Okay, you're saying okay. Then the entire thing goes into the boundary term, and that
probably.
Okay.
Probably, okay. Yeah. Okay.
Just to make a comment, like yes. This R is like a total derivative term, right? Like in 2D. That is what Gauss-Bonnet theorem says. And what happens is that when you have a boundary, that R also goes to the boundary term, I think, and then you get this genus contribution.
I see. Yeah. I have not looked into the proof.
Yeah, I know that in 4D Gauss-Bonnet invariant is a total derivative term.
Okay, I see. So yeah, so let's work with genus equals to 0, and let's do this path integral. So the very important thing here is that there's the existence of this boundary manifold. Okay, so first of all, I'm going to fix some boundary conditions. Okay, so the boundary conditions I want to fix is that when I take the bulk metric and when I induce it on the boundary, and my boundary manifold, my boundary coordinate is u. So let's induce that bulk metric on the boundary, and I'll call it gamma UU. I'm going to fix it to 1 over delta square. Okay. This is equivalent to saying that if I do this integral root gamma du, so u always goes from 0 to beta. So okay, I'm doing Euclidean path integrals where my time goes from 0 to beta. Okay. So if I do this, then this just is beta by delta, right? And this, so basically what I'm trying to tell you is that fixing this boundary condition or putting this condition is equivalent to fixing the length of your boundary. And that length of the boundary, so if it's an ADS, and if you're looking at a length of a boundary in ADS, it always diverges. So you have to put a cutoff. You have to put the boundary at a finite distance away from actual end of the manifold. And that cutoff is this delta. So as delta goes to 0, you'll see that the length of the boundary will, so this integral is length of the boundary. Okay. And as delta goes to 0, this diverges. So delta is just cut off to fix the length of the boundary. And then I'm going to put a boundary condition on my dilaton. So that boundary condition is basically that if I induce dilaton on the boundary, it should look like some constant phi r divided by delta. Okay. There are a lot of physical reasons to do this, but I really don't want to go to it because we don't really need JT gravity to understand the resolution. So there is this particular boundary condition that we are putting. And now let's assume, okay, so now let's do this. Let's start with the path integral. So path integral, of course, is going to be the function of the boundary parameter. So first is beta, and then other is phi r. Okay. And then let me write down path integral as this g mu nu d phi, and whatever I'm writing now is very figurative in the sense, formal, not explicit computations. So now I want to do this. Okay, I want to do this path integral, and the topological term, let's say, is just sitting outside. So let me put a proportionality sign here. So let's do this computation, and before doing this, let me integrate over just the dilaton field. Okay, so if I integrate over the dilaton field, this is what happens. The integration over metric remains, but you see the term here. So okay, another prescription is the path integral contour for dilaton that I'm choosing is going to be purely imaginary. So if I choose that contour, what happens is this term, which I've double underlined on the top, just becomes a delta function of r plus 2 by L square. Okay, and then the bulk term is completely gone, right? Because I've completely integrated over the bulk slices, and that gives me this delta function. And what remains at the boundary is something like this, 8 by g. And because phi, the boundary condition for phi is phi induced on the boundary is phi r, so I get a phi r over here. And then there is an integration over du. Root gamma is fixed, so gamma uu is fixed to 1 over delta square, so root gamma is 1 over delta. And phi was phi r upon delta, so that has 1 over delta again. And then you have extrinsic curvature minus 1. Okay, this is what you have. So this is what you end up with at this point as this. And now what you have to do is, first of all, I have not, so this is again on the boundary manifold. So the bulk term is completely gone, and I've reduced all of the JT gravity path integral onto the boundary. Okay, now it's on the boundary. And so in order to understand this term, this boundary term better, let me just define one more thing. And that is just the so first of all, here, this is an important condition. Okay, so as I told, as I said in last lecture also, that this particular condition, r plus 2 by L square, came out before as an equation of motion. But now you have to remember that this is not an equation of motion. This is really a delta function sitting inside a path integral. So earlier, if you have to impose that equation, you would have imposed it only on the on-shell solutions, okay, or on-shell configurations. But now you have to impose r plus 2 by L square on all the off-shell configurations. Your path integral has to be only done with all possible metrics which are locally ADS2. Okay, so the off-shell configuration space itself is reduced, is restricted by this particular delta function. So let me pick one particular very well known solution that we know, and that solution is just the Poincare upper half plane. Okay, so I'll call Poincare time as t subscript p, and then let's write this as a metric. Okay, so if I do this, then and then let's assume that my boundary curve. So let me just draw a diagram here. Let's say t. Okay, how do I do this? Maybe I should write tau. Okay, so d tau of p, and then let's say this is tau, and this is your z coordinate. Then your boundary curve will look something like this. Okay, so this here is really, sorry, this here is really z equals to 0, and z increases in this direction, and the red curve I've drawn is let's say the boundary curve. So let me put some parametric equation for it. In the sense, let me say that the boundary curve is described by tau as a function of u and z as a function of u. Okay, so this is a parametric curve in your manifold, and I'm describing it by this function. And now let's impose this condition that gamma using, okay, so using this equation, let's impose the condition that gamma uu, which using this particular metric will become okay, what will it become? It will become t prime square plus z prime square divided by z square, and all of these are functions of u. Okay, and that I have to set equal to 1 by delta squared. That's the boundary condition I have for my boundary. So what this tells me, it tells me that t of u up to leading order is just this. It's sorry, z of u up to leading order is just delta into t prime of u. Okay, and then plus some order delta cube terms. So this is some equation that you got, and that equation came from the boundary condition that you put on the metric. Okay, so but what this has done is the boundary curve is now defined. So earlier boundary curve was tau of u, comma z of u. Okay, now this boundary curve is just described by one function, and that function is just t of u comma delta into tau prime of u. Sorry, I'm exchanging t's and taus, but you know what I'm saying. So it's always tau, and now all of my boundary curve is just given by one function, and that one function is tau of u. Okay, and if you look at it carefully, tau of u is really, so this function here is really mapped from it's a map from boundary time. Okay, it's a map from boundary time to bulk time. Right, the bulk time is tau, the boundary time is u, and tau as a function of u is really that map. So so once we get to this point, now what you just do is, so now you know what the boundary curve is. Okay, boundary curve is fixed in terms of some function, and we are not imposing any on-shell equation of motion. Everything I'm doing is off-shell. I'm just trying to understand the path integral structure. Okay, so tau of u, so all possible off-shell configurations of my boundary are defined by this one function. So it's a one function family. And so in the last slide, we stopped at this expression here, and the only thing that remained to compute was your extrinsic curvature, and we couldn't compute it because we don't know what the boundary is described by. But now we know what the boundary is described by. So let's take this boundary curve and find the extrinsic curvature on this. And if you find the extrinsic curvature, you'll see that the extrinsic curvature is 1 plus delta squared into Schwartzian of T of u. So extrinsic curvature is 1 plus Schwartzian of, sorry, delta square into Schwartzian of T of u. Okay, and Schwartzian derivative is the usual,
Hi, Adwait, could you put a subscript or something whenever you're writing Schwartzian, because I thought you're also using curly brackets for sets.
Okay.
Slightly confusing.
Yeah, no, thanks. That's just useful. So let me write it as this: k equals to 1 plus delta square into Schwartzian of T of u. Okay, I'll just write SCH before the function, and the way it's defined is this: the Schwartzian of a function T of u is equal to this particular expression. It's T triple prime by T prime minus 3 by 2 T double prime by T prime whole square. Okay, now we have everything. Just plug this value of k back here. You see there's k minus 1, and then there is 1 over delta square that exactly cancel the delta square we had. And now what we are left with is integral over. Okay, the one small glitch I haven't told you is that there's small diffeomorphisms which are still remaining. So there's an integral over metric, but you can fix almost there are 3 components, and you can fix 2 of those components to using gauge fixing, just the usual Parthiv-Haldar procedure, to some numbers that you want. You can gauge fix them, and the only component of the metric that remains will automatically translate into the degree of freedom T of u. Okay, and let's not go. It's not really needed how it happens, because it's actually very subtle. It's not that simple to understand. So let me just give you the answer. The answer is z as a function of beta and phi r is proportional to some particular measure on these functions, and it just becomes e to the power. Okay, I'm a bit I forget what the sign is. Maybe it's plus or minus something. Phi r divided by 8 pi g Newton integration du Schwartzian of T of u. Okay, and hence this is the famous Schwartzian action that you get out of from in the JT gravity. And you see, we haven't done any on-shell things. We always remained off-shell, and we just started reducing degrees of freedom in our path integral, and at the end we ended up with only 1 degree of freedom, and that's this boundary, the displacement of boundary. It's boundary wiggles, and that is the only degree of freedom that you have. So your metric is fixed to some metric which is here, and the only thing you can do is cut your manifold in different types of boundaries, and those will give you different actions, and that action is equal to the Schwartzian of that boundary, that placement of the boundary. So this is the famous Schwartzian action. Yes, please.
There's a question from Subbu. Subbu, go ahead.
Yeah, Adwait, this went a bit fast for me. Can you just summarize what you did in the last 2 slides?
Yeah, I started from a JT gravity path integral.
Okay.
And started integrating out stuff, and I could reduce the whole JT gravity path integral onto the boundary. And I have what I have shown is the only what do you say, the only physical degree of freedom that is remaining is this function tau of u, and that is being identified as Schwartzian mode. Okay. And that's so all of the JT gravity path integral just reduces to the Schwartzian path integral.
Okay, I see.
Okay, so rather than doing JT gravity in the bulk, you could just reduce everything to the boundary and only study this path integral. Studying this path.
So the surface was the boundary, is it? Like this surface you have drawn as tau of u?
Yes.
And like what told you that you have to compute the Schwartzian?
Oh, I just when I reduced it, I had a boundary term which looks like k minus 1, and then the only thing that I had to compute was k at the end, and the computation of k gives you the Schwartzian. K is the Schwartzian of that function.
Okay, I see. Okay, because of that you are computing this. Okay.
Yeah,
okay.
Exactly. Yes.
Okay. Yeah. Thanks.
Okay.
Thank you.
So fine. This is.
Adwait, I missed what you said about this plus minus sign in front of in the exponential.
I don't remember the sign.
Okay.
That's what I said.
Okay.
Yeah. Just you can put.
Yeah. Sure. I thought if there is something.
No. So yeah. Good. So now I can just study this theory. Okay. And what does this theory say? What I have to do is just find out equation of motion of this theory. Okay. So one more thing I haven't told you, but probably is not important, is that while setting the boundary condition for the dilaton, I could have set a general boundary condition. In the sense, I could have made this constant fire as a function of the boundary time. Okay, but you can always set it to constant again, and it's a subtlety, but it's not really it's not really important. Okay, so now you take this and you just find out equations of motion for the Schwarzian. Okay, for the Schwarzian mode. So tau of u I'll always call as Schwarzian mode. Okay, so just find out what is the equation of motion for that. So you just do usual Euler-Lagrange procedure, and what you get is this. So the equation of motion from Schwarzian is this. It just becomes d by du of Schwarzian of t of u equals to 0. Okay, that's the equation of motion, and a simple solution to this equation of motion is that tau of u, and now let me start restoring this subscript because it's a Poincare time. It's equal to beta by pi. Beta is an integration constant.
So is it right that the action is now some third derivative action?
It's a fourth derivative action.
The Schwarzian action, right?
Yes.
And then you land on the simple equation of motion?
Yeah.
Okay.
Okay, so you have so this is the solution that you have. Okay, it's a tan solution, and now I'll just I could have described the whole story till now in Lorentzian signature, but path integrals are tricky in Lorentzian signature. So you get to the equation of motion first, and now I can analytically continue this solution to the Lorentzian section, and this is a Euclidean solution. Okay, and then if I write down a Lorentzian solution, that Lorentzian solution looks just it just analytical continuation, and tan becomes tan hyperbolic, and that's it. Okay, just analytical continuation of u. So yeah, this is your Lorentzian solution. Okay, and then let's try to understand what Lorentzian solution is. And another thing I wanted to point out is that all the solutions of JT gravity are black holes. All the solutions. Okay, it's only if I go, let's say I take beta going to infinity limit, which is the 0 temperature limit. So if I take the 0 temperature black hole, I get TP of u is equal to u. Okay, I get u, and the point is this is still an extremal black hole solution. Okay, 0 temperature black hole. So this is an extremal black hole solution. But all solutions to JT gravity are black holes. JT gravity is somehow tailor-made to just describe black holes. Okay, so good. So you have I have described you the solutions, and let's try to understand what the solutions are. I keep in mind that in this slide I had matter also here. Okay, I had matter here, and so the equation of motion that we found here, okay, which is this quadratic operator acting on the dilaton equals to the matter stress tensor. Okay, so this equation of motion, okay, so this I won't explain it more, but I just want to say that this equation of motion and the equation of motion we found out right now, which is the derivative of Schwarzian equals to 0, are equivalent. Both of them have exactly the same content. Okay, the only change would be the right hand side of this equation won't be 0 because there would be matter. Okay, so that's it. That's the only change, and yeah, that's it. So
how did you conclude that it's a black hole solution? I didn't get that.
Yeah, I'm going there. So just next slide. So let's look at different solutions and how these solutions look. Okay, so now what I'm doing is I'm looking at a metric, which is the global, and I'm starting to looking at, I'll only look at Lorentzian objects. So let's look at the Lorentzian global ADS2. Okay, and this is some the metric looks like this, sine square sigma. Okay, so that metric basically is this, all of this yellow patch. Okay, this the Lorentzian the global time goes from -π/2 to +π/2 here, and the sigma coordinate here goes from 0 to pi. Okay, and this describes all of ADS2. Okay, so not exactly really, that if the time goes up till, let's say, up till pi and down till minus pi, that whole manifold, so this whole strip is a complete description of ADS2. All of ADS2 is described by this thing, but I have only drawn here till pi by 2 and minus pi by 2. Okay, and that's because the black hole solution only contains this. So let's look at now. Let me just give you what does it mean by black hole in these 2D theories. Okay, so first of all, let's assume that just sorry, I apologize. So yeah, so let's say you're fixed, as I said, that this r plus 2 equals to 0 is a path integral condition. So I'm fixing a metric I want, and that metric is the global ADS2 metric. Okay, and global ADS2 contains all of the ADS2 patch, so I don't have to worry about, oh, maybe I'm missing out on some of the ADS2 manifold itself. So it covers all of the ADS2. And let's say that, so now because global ADS2 has two boundaries, so there's one boundary at sigma equals to 0 and one boundary at sigma equals to pi. Okay, so that means in the earlier description where I was just looking at Poincare ADS2, I only had one boundary, but now I have two boundaries. So in the sense that, so I'll have two functions. So maybe let me call it T left as a function of u, and T right as a function of u. Okay, and I'll have two of these boundaries, and let's say these are all counterfactual arguments, in the sense that I don't know if these are solutions or not, but let's assume, let's say I get two of these solutions, and the Lorentzian version, which looks like this. Okay, not this exactly. So let's say in this I plot the functions that I got as a function of u. Okay, and let's say I get these two curves. So one curve is here and the other curve is here. Okay, and that's it. That's the solution that you get. So what happens if the solution is like this is that you automatically create points in the bulk. Okay, so let's say this point, you automatically create points in the bulk which can, so let's only look at the right boundary right now. From this point there is sorry.
I have a question.
Yes.
You said there are two boundaries.
Yeah.
I thought sigma was identified.
No, time is generally identified, but this is a universal cover.
Oh, so the sine sigma?
Yeah,
I thought that defined.
pi.
I see. Oh, okay. I see.
The manifold starts from sigma equals to 0 and ends at sigma equals to pi.
I see. Okay. So, I understand. Okay. So you basically cut open the global ADS and uncovered it. Okay.
Yeah. So let's just look at these two, and let's take a point in the bulk. Now you see this point can only send signals in its light cone. Okay, maybe in the future, if it's sending, it can send it in this light cone. If it's sending in the past, it can send it to this light cone. Okay, that means this point can't ever communicate with the boundary of our region, right? Whatever this boundary is, there is no possible way that a signal can be sent from this point to the boundary. And it's all in this example, it's also true for the left boundary, that this point cannot send signals to right or the left boundary. Okay, so automatically the structure of the boundary creates regions in the bulk which cannot communicate with your boundary particle, which cannot communicate with asymptotic. And this we would take as a definition of what means to be what it means to be having a horizon. Okay, horizon, beyond horizons are the region which cannot communicate with asymptotic boundaries. Okay, so if you look at these examples, you'll see that there can be examples where, so first of all, this is an example where there exists a horizon, and there's more than that. The two boundaries cannot communicate with each other because the light cones, so these green regions are the regions, the green regions mark the horizons of the left and right boundaries. And those are the only exteriors that are available to left and right boundaries. Everything else is the interior. Okay, So in 2 dimensions, there are no real singularities. Okay, and as I think I've sort of hinted earlier, that black hole information paradox has nothing to do with singularity. It only has to have a horizon across which a pair production is happening. Okay, so this setup is good enough. So just the description of the boundary tells you whether horizon exists or not. More specifically, if the boundary curve hits your if the boundary curve hits the manifold, the end of the manifold at some finite bulk time, then you can draw a 45-degree line back from that, and that creates a horizon. Okay, that line will be identified as a horizon. So in this example, 2 boundary particles cannot communicate with each other, but it could happen that you are in this situation, okay, where one of the boundary curve is large and the other boundary curve is small. Now you can see that there are these red dots. So there is a possibility that you can communicate from left boundary to right boundary. Okay, and this is what people call in 2 dimensions to be wormholes. Just the fact that the boundary curve structure is such that 2 boundaries can communicate with each other, and that just means that there exists a wormhole.
Adwait?
Yes.
Rohan, I think, has a question. Rohan, go ahead.
Yeah, so you did a some sort of an analytic continuation while going from Laurentian to Euclidean, right? I mean, even the charts got extended because now you seem to have like 2 boundaries. So you've done sort of like a thermofield extension, if you think of it in terms of the original thing. That's what is going on. Right? So now you don't need to do a further thermofield extension. This chart thing that you used to embed your earlier solution to this already does that.
Yeah, that's true. That's true. So, I mean, the whole story, I'm saying in my head, you should only look at it like this. So either you can work with Lorentzian or Euclidean section. And then this R+2 condition tells you work with locally ADS2 manifold. So you work with locally ADS2 manifold. And now on top of that, you have to look at solution of your boundary manifold. So you just look at how the boundary manifold behaves, and the behavior of boundary manifolds tells you whether there are black holes or wormholes or whatnot. Okay, so that's it. So yeah, I think the point you were saying, I'll come to it in some time. Okay. So now let's look at the solution that we have obtained.
Sorry. Can you just go back to the previous slide?
Yeah.
Yeah. What do you mean by these 2 boundaries can communicate through these wormholes? I mean, I can see that the signals from both of these boundaries reaches a bulk point, which is where they're intersecting. But no, they can't still communicate with each other.
It's the right hand side, or the right hand side diagram can communicate. I've drawn a 45-degree light like ray, which goes from one boundary to other boundary. So this is a wormhole, and there's no wormhole here. Okay.
Karan, you had a question. Please go ahead.
Yeah. So these are a specific class of traversable wormholes. Because in the normal wormhole sense, you can't send signals from one side to the other. I mean, causal signals don't go from one to the other. You can send light rays and they'll sort of end in the throat. But here you're saying that you can send a signal which goes from one side to the other. So, I mean, it's a 2-part question. One, is it a traversable wormhole? And 2, why are you calling it a wormhole if I can't see how the 2...
What? The answer to the first question is yes. Second question I didn't get.
Sorry, Karan, we lost you.
Yeah,
the second question.
The second question is basically in the wormhole case, you can see that these are that if I draw, so take your left diagram, you have these 2 horizons, and the wormhole part would be basically telling you how the 2 sides are basically connected in some sense. So how does your left map into the right, where you can see, okay, this is the horizon of the right guy, and this is the horizon of the left guy. It seems like they overlap with one another. So how are you really classifying it as a wormhole in that sense? Like what is the horizon? Okay, so to rephrase the question, what is the horizon?
Yeah, go ahead. Hi, go ahead.
Sorry, Karan, we lost you again.
I'm sorry, did I go through? The internet is a bit...
Yeah, no, I think we lost you there. So you were saying
you lost me again. Yeah, so I mean, here it looks like the horizons overlap in the right diagram. So in what sense are you classifying it as a wormhole? I mean...
See, the wormhole is whether there is a connection from left to right or not. So you can have a wormhole, and it might not be traversable, but So okay, I'll tell you what so the wormhole on the right hand side that I've written. So if the horizons overlap, it's a wormhole, clearly. Okay, and if they overlap, so there is a limiting case. That limiting case is this, where they just overlap. So this is a wormhole, but it's not a traversable wormhole. It's a non-traversable wormhole. Okay, but there is a wormhole here. In this case, there's a wormhole on the right hand side, and it's also traversable because horizons are overlapping now. Okay, and all of this structure is just determined from the way your boundary curve behaves. That's it.
Okay. Yeah. Thanks.
Yeah.
Okay.
So,
Tushar has a question. 1 second,
yes.
Adwait.
Yes. Tushar, go ahead.
He's unmuted, but we can't. Tushar, we can't hear you.
Is it okay now?
Yeah.
So can you go back to the previous slide?
Yes.
So here I have two questions. So firstly, the temperature of this black hole, can you express it in terms of TL and TR, right? It will be some function of TL and TR. So how do you write the temperature?
Let me say this, that the examples I'm giving are counterfactual examples, in the sense that these are made up examples. I don't know if such an example exists or not, but the reason I'm giving you examples is to tell you how do you understand whether there is a horizon or not, or understand whether there's a wormhole or not.
Okay.
That's it.
And,
so okay. I don't think such solutions will ever come in pure JT gravity. You will have to add some sort of matter, or you'll have to add some sort of extra interaction between left and right boundary in order to create such wormholes. Okay, but even if you do it, the degree of freedom always remains to be your boundary degree of freedom, and that degree of freedom always dictates where the horizons are and whether you can communicate with left and right or not. Okay, that's all I wanted to. That's the point I wanted to make. Now this diagram here is a real solution, and that real solution is what we wrote down. Okay, the solution that I wrote down, which is beta by pi tan hyperbolic pi by beta, is this solution. Okay, and it looks like this. So the left and right curves are exactly same to each other. Okay, I mean they're similar to each other up to SL2R degree of freedom. So you can use SL2R. So SL2R is a remaining symmetry which is still there. Yes. It's not important really, but it's still there, and you can make them exactly look equal to each other. And this is the solution of eternal black hole in ADS. Okay, so but the thing is, yes.
So I think Arindam might have a follow-up question or a question related to that. Arindam, go ahead.
Sorry.
Yes.
So my point is that I understand that if you look at from the position of these boundary curves, that there are some regions of the bulk that you cannot cannot communicate to, right? So in that sense, but why are they? Why are you calling them black holes? Why aren't they not, for instance, some cosmological horizons or something?
I don't know. Is there? I mean, if you, I would say that these are geometries with horizon, which don't really have singularities. But the way I understand it, the black hole information paradox is only to do with horizons and nothing to do with singularity.
So just the fact that these horizons exist, and if you say that if there is some pair production happening around them, then you.
Okay. I mean, you can associate a temperature with the horizons, and that temperature is beta, which that defines the temperature in your solution. And I'll tell you how. So okay, first of all, I'm mixing up coordinates, but in the global coordinates, this is how the global eternal black hole ADS2 looks like. And maybe it's not appropriate to write this solution here, so let me just cut it. And this is the correct solution. Okay. Okay. So the solution that we wrote down. So what we did was we started with the Poincare upper half plane, right? Which was just dA square equals to minus dt square plus dz square divided by z square. This is the background that I fixed, and that this curve here is just this region. Okay, everything in this diagram except the blue regions, everything shaded which is not blue is described by this patch. Okay, so so the sigmas and t's are the global coordinates, and so sigmas and tg's are the global coordinates, and tp and z are the Poincare coordinates. So the whole, all of the shaded region is global ADS2. Okay. Now the shaded region, which is not blue, is Poincare wedge. Okay. So Poincare wedge, in that this line is z equals to infinity. This line here is z equals to 0. Okay. And the curve which is here can be drawn in this diagram like this. So it starts from here and ends up here. Okay, maybe I don't know. I should just take something. Yeah. So it starts from here and ends up here. Okay. So this is the curve that is described by this solution. Okay. So as I told you, why do I call this black hole? Because it just creates a horizon, because these curves are hitting at z equals to 0 at some finite time, and it automatically creates regions in the bulk which cannot communicate with this region. Okay. Now the diagram that I drew before is also the same, but it's just that what I have done is I've drawn some Poincare wedge from here. Okay, and it just goes beyond this surface, and it just does this. So I have such a big diagram where if I only want to describe this part, okay, then this is how I draw it. So like equivalently you can, so this is the right Poincare wedge, equivalently you can start describing something on the left. Okay, and the equations would look exactly the same. So this is the black hole solution, and these 2 points here are TP equals to beta by pi, sorry, minus beta by pi, and this point here is TP equals to beta by pi. Okay, and that's how these temperatures are associated with horizons. All right. So now and okay, that's what the solution to that's how the black hole solution looks. And also to say that this was
Can
a
I
solution.
ask a question?
Yes.
Yeah, so even if you started with the global coordinates and redid that analysis, you would land with the Scholzian action, but 2 copies of Scholzian action.
Yes, yes.
Okay, okay.
So this is a vacuum solution. Okay, this is a solution without any matter. This is a vacuum solution. So all the solutions that we have described here are vacuum solutions. So and we would like to start with this solution first of all. And
Can I make another question? Like
yeah.
So what I don't understand is when you have two Poincare patches which are like, if you do that for global coordinates, and I'm confused about getting 2 independent Scholzian actions. They have to be consistent, right? Because the Poincare patches overlap. In say usual thermophile double or something, I can make independent boundary conditions at left and right, because the horizons, the right and left wedges don't overlap. But it seems the right and left Poincare patches overlap. So I don't seem to get independent boundary conditions for tau right and tau left.
You just have to do it. You will get it. This is what I would say. And you would say that, okay, it seems like these are 2 independent Schwarzian, then what does even restrict? I mean, how do you even correlate left and right in some way? Okay, or what is the restriction on left to right? So what you have to do is you have to compute some global SL2R charges. SL2R is still a remaining symmetry. So you have to compute some global SL2R charges and set them to 0. So if you do that, then left and right solutions are only related by some sort of SL2 transformation. And you could do that. But okay. So
there are independent left and right taus. That's the claim, no?
No, they get connected to each other by charge conservation equation.
Oh, okay. Thank you.
Because the global EDS2 has SL2R isometry, and that has to be preserved. Okay, so fine. So now I've described you how solutions in JT gravity come about. One small thing I wanted to say before I go on to constructing the model that I really want to construct is that let's look at a general gravity theory. Okay, and what you do is, so it looks something like this. Let's say some ddx, and let's put some matter in it. Okay, so let's put some matter in it. Now I've showed so equations of motion coming from this theory are just Arminu this. Okay, I'm going to do this again. So T mu nu equals to 8 pi g T mu nu. Okay, and if you're really considering quantum theory, then you have to also specify the state and you have to also say what is the, you have to basically replace this by expectation value of the stress tensor in that state. Okay, so you have to really specify what the state is. Now, so clearly here, what has happened is this part, the left hand side of Einstein's equations come from here, and the right hand side of Einstein's equation come from here. Okay, and you can see that if I send G Newton to 0, I can if T mu nu is not of the order 1 over G Newton, and the energy densities are small, then I can ignore the back reaction in the limit where, so when we say G Newton going to 0, this is the classical limit where Einstein's equations are valid. Okay, and in that limit, I can always ignore back reaction if T mu nu is order 1 object. Okay, order 1 object in the sense it doesn't scale with G Newton. Okay, so this is what generally happens. But let's assume a scenario where your S matter, okay, is some n free scalar fields. So let's say it's some n minimally coupled scalar fields, and let's say that these are, okay, not n, let's say these are C coupled fields, and let me write it as just free scalar field. Okay, this I index goes from 1 to C. Okay, now if you find out the T mu nu from this expression, you'll see that this T mu nu would be order C. Okay, it's an order C expression. So now when I again write down the Einstein's equation, what will happen is I'll have 8 pi G into some C and into some, this is all very loose arguments, but you'll have some number or a function here. Okay, but now what you're going to do is you're going to send G Newton to 0. Okay, but what okay, but there is a possibility that I could send G Newton to 0. I could send C to infinity, such that G Newton into C is some fixed number. Okay, is this true? Is this clear? So if I do that, then I can take account of back reaction. Now back reaction, basically what I have to do is I have to scale C with 1 over G Newton somehow, so that the right hand side of Einstein's equation doesn't go to 0, and I can start taking into account back reaction. Okay, but there is a range of C. You can keep C, so you can work in this limit where G Newton is much greater than C, but it's much greater than 1. Okay, what happens is that in this limit you can ignore the back reaction. So what this is, can I ignore the back reaction? Just a minute. It's much greater. Yeah, in such a limit you can ignore the back reaction, but the number of fields are still enough to contribute to some other effects, and that other effect is something like entanglement entropy. So let me just write one more slide in order to make this more clear. So as I've shown you that entanglement entropy is just computation of I mean you can start to compute entanglement entropy by computing rho to the power n, which is just a partition function on an n-sheeted Riemannian surface. Okay, so let's say I'm working in some classical limit, and let me only look at contributions of contribution to the action on this n-sheeted geometry. Okay, so let me fix the background to something, and then I would like to write down gravitons. Okay, I mean I would like to consider gravitons also. So the action would look something like this. There is a 1 over G Newton part to which is just S naught, which is just comes by substituting G naught into your action. Plus there is a second order action which comes from which is basically the 0th order metric, but it also contains gravitons. And then there is a matter action which is proportional to C, and it only couples to G0. So these are the first 3 leading order terms. Okay, so now in this limit, you see this object is order 1 over G Newton, this object is order C, and this object is order 1. Okay, so first of all, this is your pure gravity contribution. Yes.
There's a question from Subbu. Subbu, go ahead.
Adwait, in your previous slide, when you said T mu is order C, how did you get that? I mean, is it the usual T mu computation? Because then I can't see how you will get a C term, a C factor. You just vary with respect to G, right?
Yeah, I would just.
How will you bring a C from the summation?
I mean, you'll have to do some coordinate changes. You'll have to.
Are you evaluating it on a? Are you evaluating it on something? The T mu.
So there are simply C fields, no?
So, yeah, but how will you get T mu to be proportional to C? That is what I'm asking.
You add the T minus of independent C scalars, I thought.
So, okay. I see. Oh, it's just the numerical factor. Number.
Oh yeah,
Okay.
Yeah.
I see. Okay.
So then there is a maybe.
Adwait, maybe not this read.
Yeah. That's what I did.
Okay, one sec. So I'm
this
still
is
confused. Sorry. I mean, okay, one sec.
Yes.
Can you go back?
Yeah.
Yeah. So I mean, for each of them, the energy momentum tensor will come in terms of phi I, right? Like, I mean, it still won't be like adding a number of the same terms. Like,
no, what you can do is you can go to this coordinates like average and difference coordinates. Okay. In that, you'll see that explicit action terms itself will have a C sitting outside. That's what I realize it's a bit more complicated to explain this way. That's why I went to the second slide, where I've already written that the matter action here already has a factor C sitting outside.
Okay, then that would be okay, because here, like, I don't see like how you will get a C.
Yeah, I understand what you're saying, but
okay.
Yeah. So, and then there is a graviton. So this is a part which is graviton action. Okay. And this is a part which is matter action. Okay. So as long as I work in a limit where C is much greater than 1, but 1 over G Newton is much greater than C, I can ignore the back reaction and I can ignore the gravitons also. Okay. That's the limit I really want to work in. Okay. I really want to work in this limit where the limit is 1 over G Newton, which is much greater than C and much greater than 1. Okay. This is the limit. And the thing is, in higher dimensional gravity, the number it's always 1 over G Newton. The equivalent of this in JT gravity is really phi R by beta. Okay, so it's phi R by beta, much greater than C, much greater than 1. Some dimensionless number here, and we'll use this limit at some point. But I just wanted to, all I wanted to communicate to you, even if you haven't understood this fully, all I wanted to communicate with you is that there's a limit in which I can hype up the contribution of the matter, but still let it not back react on the background. And also so you could just think of that I'm doing this in order to ignore the graviton contribution, you see. So if I want to ignore the graviton contribution and only consider matter, then I can just do this where I make this C large such that all the order 1 contributions are ignored. Okay. And I showed this in action, but action on an n-sheeted manifold is the same as Rene entropy, and the analytical continuation is the same as entanglement entropy. So just a rough argument that in what limit graviton contribution to the entanglement entropy can be ignored. So this is the limit in which graviton contribution to the entanglement entropy can be ignored. Okay. All right. Now let's just look at how do you construct Euclidean black holes, and how do you prepare states in, let's say. So here I am just assuming that
I think Karan has a question. Karan, go ahead.
Yes, please.
Yeah, just coming to your last point. So, so isn't this essentially what the last slide? I mean, when you're saying C, those limits that you've described, isn't this just the ordinary setup that we have for, by ordinary, I mean, like, it's the large n limit of ADS CFT where you're ignoring, I mean, you're not considering 1 over n corrections for the matter fields in some sense, because 1 by G Newton is related to n.
I mean,
it's different from that. I mean, it should be the same, right? I mean, that I think that is essentially what you're saying.
Yeah, but I'm just saying in ADS CFT, the places where matter contributes, in general, you'll see that the gravitons will also contribute. So unless you have a large C CFT, so just to make this very clear, this is something unheard of. I'm putting a large C CFT in the bulk. It's not a boundary CFT. A large C CFT is on the bulk, and that's why contribution coming from that large CFT is much greater than the graviton contribution, which comes at order 1, but it's not as large as 1 over g Newton, so that it's enough to back react. That's the point.
Okay, and follow-up is on this entanglement entropy that you just mentioned. So,
yeah,
are you saying that you don't need to consider?
We lost you again.
The correction that you talked about earlier? I mean, that point you just mentioned.
I couldn't hear a lot of your question.
Yeah, you mentioned that we can ignore, in the entanglement entropy point, you mentioned that you can ignore the entropy of the fields in some sense. So are you saying that you're not going to consider the quantum Ryu-Takanagi, or?
No. I'm saying that in general, if I don't have a large CFT or if I don't have n number of fields, I can ignore it because the contribution is order 1. But now I'm putting, and see, when I say fields on the bulk, which all come at order 1, they can be graviton fields, they can be matter fields, and all kinds of fields. But now what I'm doing is I'm taking a particular field, which is not graviton, and I'm putting lot of them. Okay. So suddenly contribution of those fields becomes higher. And when these fields are present, I can ignore gravitons. Okay. Because gravitons are much harder to deal with. That's why you want to ignore gravitons. So that's the only logic, nothing else. It's still a probe approximation, but it's a stronger, it has a stronger contribution than graviton itself.
Okay, thank you.
Okay.
I have a question.
Yes.
So when you say that you're neglecting gravitons, do you mean that the diletons? Because in 2D I thought there are no gravitons, right?
Dileton and also Schwarzian.
Okay.
The T of U. So
right.
I just solved for equation of motion of T of U and set it to that, right?
Right.
But
right.
I could have looked at one loop determinant around the Schwarzian action, which I'm not doing.
I see. Okay.
So
okay.
I'm not considering fluctuations around the saddle point of the Schwarzian.
Okay.
Can I just confirm one thing based on last question? When you ignore the diletons, I thought dileton is proportional to T mu nu by equation of motion.
Dileton is proportional to T mu nu by equation of motion.
Right. That was your G equation of motion, no?
Sorry, say that again. The dileton is proportional to?
I thought some operator, linear operator acting on dileton is proportional to T mu nu.
Yeah, if I have matter, yes.
Right. So I was just comparing that with your previous statement that you can keep T mu nu but ignore dileton, as in ignore gravity. I mean, going off or
dileton is integrated out.
No, but I'm saying that it's just the limits. That's it. So if the right hand side is much maybe if right hand side is suppressed by that action in that equation, I can just consider that right hand side is almost 0 or negligible. Right. So the thing I wrote down here, right, this equation. So this basically says that 1 is much greater than C into G Newton. Okay. And you'll see that the right hand side of that equation was G Newton into T mu nu.
Yeah, I was comfortable with this statement, but then when you said you can ignore gravity and that means ignore dileton, I got confused because I thought dileton was proportional to T mu nu in some sense.
It is, but it's not proportional. There's some quadratic operator acting on the dileton,
right,
is equal to this, right? But on the right hand side, because there's a T mu nu, you will have G Newton into C, and that is still small in this limit. So I can just take this equals to 0.
Oh, okay. There was these things. Oh, right.
Yeah, and this kind of limit will also enter your fluctuation action. In the sense, action, if you're expanding an action in these limits, you will see that the fluctuations of dileton and the fluctuations of the Schwarzian, which are called boundary gravitons in 2D, are always subleading. So I can ignore it. All I have to look at is this first term and this third term, which is also what really enters. Anyway, so this is what I wanted to do. Okay, so whenever we are doing thermal CFT, what we do is we put a CFT on a circle. Okay, and if I have a 0+1 dimensional CFT, then that's the only thing there is. So it's just a circle. Okay, so this is CFT1. It's a thermal CFT, and the length of the circle defines the temperature. Now, when we are doing ADS CFT, what do? We basically fix boundary conditions, and then we fill up the bulk You basically put some metric such that those boundary conditions which are described by the CFT are followed by that in that metric. Okay. So one of the Euclidean solution, which is Euclidean black hole, basically looks like this, which is also described by, which is the right hand side, which is also Poincare disk. Okay. And as I said, the boundary, our boundary theory has a peculiarity that it lives on some cutout, right? It lives on some manifold which is tau of u comma r of u. Okay. So the ADS CFT works like this. So it's a theory on circle, and then all you have to do is it's basically that it lives on these wiggled manifolds. Okay. So if you have a disk or different tau of u, we'll just define different cutouts of this disk. Okay. Now this is a Euclidean path integral which I have written. So this is a Euclidean path integral, and if you cut Euclidean path integrals, which I was saying yesterday, roughly, that if you leave a Euclidean path integral open-ended, then it creates a state. Any path integral open-ended, then it creates a state. Okay. Now leaving open-ended is the same as cutting it somewhere. So I can take this circle and I cut it at this line. Okay. So when I cut it at this line, I basically get two ends. Okay. And then there are two states which live here and here. Okay. And I can combine them. And this is basically a pictorial representation of what a thermophile double is. So a thermophile double is a cut on a circle which cuts at 2 points, and the open ends are two open ends, and hence there are two. It's a state in a dual field theory. Okay. There is some more technique to this, but basically this is it. You have two Hilbert two states created here and here. But the thing is, because it's going this way, one of them is a bra and another is a ket. So you just start, you just dualize the bra and also start calling it ket. And then it's a state in a dual field theory, which is identical. And one of them is a CVT conjugate of the other one. And then it's a TFD. It's a thermophile double state. And that's how you create a thermophile double state using Euclidean path integrals. Okay. Now you can take a thermophile double state, and then you can start evolving that state in Lorentzian directions. So if you evolve that state in Lorentzian direction, you will be basically evolving two separate field theories, two separate CFT1s. Okay. So this is a slightly harder thing to grasp, that we really have one CFT1 here, and then we cut it, and then now we are saying there are two CFT1s, but it's just a reinterpretation of the same thing. Okay. So what you have is, you have these two states, and if you just evolve this in Lorentzian time, so the Hamiltonian would be some sort of HL plus HR. Okay, two Hamiltonians of the same copies of two Hamiltonians, two copies of same Hamiltonian. Sorry. Now let's look at what happens in the bulk. So if I have, this is what I described as ADS bulk of the boundary theory. So you cut the ADS bulk also in order to get a state. So when you cut the ADS bulk, you get a state on this bulk section here. Okay. And these in the literature are generally called Hartle-Hawking states. So if you cut the gravitational path integral, you'll get Hartle-Hawking states. Okay. And these states are bulk states, by the way. So what you're doing on this brown patch here is a gravitational path integral. So on these things, you're just doing a CFT path integral. Okay. But on these brown patches, you're doing gravitational path integrals in order to create the state. So you start from this and you just go integrating up, and then you stop here and then leave it open-ended, and that will create a state for you. Okay, so that creates a Hawking-Hartle state. And then you take that Hawking-Hartle state and evolve it in Lorentzian direction. So if you evolve it in Lorentzian direction, what happens is that you have these boundary curves, which is a peculiarity of these two dimensions. What happens is this boundary curve starts and ends up at some point. This boundary curve starts and ends up at some point. And then so the things that have been okay, pictorially, I'm connecting a Lorentzian manifold to a Euclidean manifold at this slice. Okay, which can be done if you just if it follows this Israel junction conditions and all. So this half disk and this Lorentzian manifold, which is just the upper half diagram of the two-sided black hole, which I had described earlier, is just connected by this. So a Lorentzian two-sided black hole is just generated by a Hartle-Hawking state by analytical continuation. Okay, you just do an analytical continuation of this disk geometry and you'll get a Hartle-Hawking state. And this part of the geometry is a Lorentzian geometry. Okay, and this is how generally in ADS-CFT you generate two-sided black holes. So this is just a quick review of those things. And now maybe, okay, so now what do we have? So when I said in this slice, when we were looking at what you can do is, if this is t equals to 0 slice, okay, you can just replace the lower half by this Euclidean circle that I said, and by Euclidean circle that I said, and you can write the complete geometry as this. So you take this geometry, and so generally you will see these diagrams around. This is how the diagrams are drawn for eternal black holes, where this geometry is Euclidean geometry, and then after this you just analytically continue. So the part which is here is the Lorentzian part, and then maybe the part which is here is the Euclidean part. Okay, so this is how you create states, and you generate Lorentzian geometries. All right. So one peculiarity. So let me just look at the Lorentzian two-sided black hole, which looks like this. Okay, and from now on, I'm not going to draw boundary curves. So you know what I'm talking about. This is a geometry, and this geometry is basically a result of where the boundary hits the actual boundary of the manifold. So I have this black hole here, and this black hole also has, I mean, whatever description I had given before of pair creation, it's still happening here. But the point is ADS has some repulsive potential, okay? And that's why radiation never goes off to infinity. So whatever radiation is coming out, it never goes off to infinity, it always falls back in, okay? So in order to fix that, what you would like to do is that attach some patch here. So let's, what you want to do is attach some patch to the left and right, okay? And then put some transparent boundary conditions at these ends. Once you do that, what you will see is black hole will actually start exchanging energy with these systems, okay? And this is a conceptual understanding of how you can create an evaporating black hole, how you can make a black hole actually evaporate away, not away, evaporate in an ADS setting.
Mathematically, what is transparent boundary condition? How do you put it?
Yeah, we're coming there. So I'll just tell you what it is. And by this idea was available in some 2014 paper by Samir Mathur. Okay, and this is the idea which has been made more and more mathematically precise. Is this, that so you have this diagram which I just told you. So one thing I wanted to say is that when you look at this geometry here, it's a black hole sitting in the middle, and then there are bath which I have attached. So I have attached a asymptotically flat half space on either side of my black hole. Okay, I'll make this more and more precise, but right now I just want to tell you how the construction starts. So I want to imagine this space-time. I want to imagine that my ADS space-time is connected to some half space, and which is asymptotically flat. So that's why the Penrose diagram of that construction is just this, and let me call this bath, because that is where my ADS black hole will send out radiations. Okay, but there is a second point of view. So this is a completely 2D point of view. Okay, because all of this geometry is 2D. There is a 2D ADS2 black hole sitting in the middle, and then I'm somehow I want to attach a bath. I want it to exchange energy with some other system. Okay, and I want to construct this model. But at the same time, I know that whatever is in the middle, whatever is here in this region here, is really dual to just two one-dimensional CFT systems, right? So that picture is equivalent to, is ADS CFT dual to this picture. Okay, what I have done is everything in the middle is just being replaced by two CFTs, and these two CFTs are these lines. Okay, these purple, I guess, yeah, these purple lines. Okay, so these two pictures, the above picture and below picture, are ADS CFT duals of each other. Okay, the point is the bath is not holographic at all. The bath, I mean, you can consider it to be holographic, and then okay, it creates a lot of extra constructions, but I don't want to. That is where the 2D 3D holography comes in, but let's just stay in 1D and 2D. Okay, so this model is what I call so this
I think we lost Adwait.
Yeah, I mean, he's still on the call, but like his video is frozen.
No, that's what happened last year as well.
The screen?
Yeah.
Okay,
yeah.
good. So, all right. So what I wanted to say is that this lowered figure is what I'll call a 1D point of view. So this is a one-dimensional point of view, and the ADS CFT dual of that is this two-dimensional point of view, where all I have done is replace the one-dimensional CFT by its holographic dual. So a two one-dimensional CFTs creates a black hole, and hence that creates this particular picture that I've done above. So yeah, let me just stop for a minute and ask you guys if this construction, I mean, whatever I'm saying right now makes sense. I'll make this construction more and more precise.
There's a question from Karan. Karan, go ahead.
Yeah, can you hear me? Hello?
Yes.
Yeah, so I just wanted a clarification on two things. The first is when you're saying asymptotically flat, do you mean flat or asymptotically flat? Because I mean, in some sense, you could flat, right? So there's no coupling of the CFT with any gravitational degrees at that intersection point. Okay, so it's just flat. Okay, and the second is that what is the are there any specific points on boundary conditions and normalizable modes, non-normalizable modes, which are important here, or that will come later? Okay, fine. Thanks.
It'll come, yeah. Okay.
So, Shubham has a question. One second.
Yes.
Hey, hi. Are the two copies of the CFT coupled with each other, or is just like?
No, they're not coupled. They're not coupled.
I see. All right.
That's where the only thing they can do is they can produce an eternal black hole. I mean, if you couple them, then this kind of example that I was given before, where horizons can do random things, that happens. But if the two copies are not coupled and the state you are considering is a thermophile double state, then it creates the geometry which is above in yellow.
I see. Is there any reference for? I suppose this is more general, right? This thermophile double construction, like. And
yeah. I mean, let me go ahead and we can probably talk about what exactly the reference that you're looking for. Okay, so this is what you have. So I think conceptually I wanted to tell you what the construction is. So this is what the hybrid holography, this is what I call hybrid holography model. In the sense you're coupling two systems. Well, I've not really coupled any other system. All I've done is extended the manifold. But now what I'm going to do is I'm going to put a CFT2 on all of this manifold. Okay, so all of this manifold will have a fields going in and out. So you just look at the above diagram, and I'll put a CFT2 on this all of this manifold. So there'll be fields going in, there'll be fields going out, and so on. Okay, so maybe more. If I draw realistic diagrams, there'll be some Hawking radiation going out, there'll be some Hawking radiation coming in, and this will also keep on happening here and here. Okay, so they'll just exchange. So if I put a CFT2, you'll see that the CFT2 can very freely go in and go out everywhere. Okay, and this is the manifold that I want to construct. All right, so let's see how do you exactly construct this manifold. So the point.
I think Karan has another question. Karan, go ahead.
Yeah, please.
Yeah, I'm sorry. This is just something that is little. So, okay, so suppose I draw my nice slice construction like you were talking about earlier, which goes from the left to the right, now starting at I0 and ending on I0. if you don't have gravity in the blue regions and you have it in the gray, isn't there an inconsistency there? Or, I mean, is this just like a schematic thing and I shouldn't be thinking about nice slices anymore? And, that was in the past. And
no, you should be. You should be.
So
let me
how
go
do
ahead
these slices?
Yeah. I see. I'll make this more precise. So, all right. So and the reason I can construct this is that the claim is that this manifold is conformally flat. Okay. What does that mean? That just means that all of this manifold can be made flat up to a conformal factor. And now let me come to that construction. That construction looks like this. Okay. So the diamond that you see is a 2D flat space, a 2D flat space. Okay. And now what I'm doing is that I'm going from, so in a 2D flat space, I can just construct real coordinates, right? Oh God. Okay. Let me, sorry. So what happened is that because power went out, I don't have my notes in front of me. I hope I've written it down somewhere. Okay, good. I have it. Yeah. So what I'm going to do is that I'm going to, so first of all, let's start from this diagram here, and let me tell you coordinates, which, so maybe I should just add a diagram here. Okay. How? Okay, I just have, yeah. So let me just tell you this construction, and then we can stop probably, because I think time is running out. So
Adwait, you can take 5-6 minutes extra if need be.
Okay, I see. Yeah, thanks. Okay, so let me take this diagram and let me start describing the coordinates. So first of all, this all of the brown region is the Poincare wedge. Okay, is the Poincare wedge. It's more precisely the right Poincare wedge. Okay, and the metric for this right Poincare wedge. So now I'm going to be writing in this x plus x minus coordinates, but it's the same Poincare upper half plane metric. So it's dx plus dx minus divided by x minus minus x plus whole square. Okay, and these are basically t, and so x0 and x1 are t Poincare and z coordinates. Okay, so it's basically dt square minus dt square plus dz square divided by z square. So Poincare upper half plane. Okay, I can also find out the solution for dilaton, and the solution for dilaton looks something like this. So this phi naught is the same phi naught which was there in the topological part. So this is phi naught, and then I can write it as maybe, let's see. I can write it as 2 phi r. Phi r is the boundary condition, is the parameter that appeared in the boundary condition, and I can write it like this. So these solutions are completely valid on the Poincare wedge, which is described by the brown region. Okay. Now let us come to the shaded region. Okay. So shaded region is the part which I as I've explained before, is the exterior of the black hole, or the exterior of the horizon. Okay. So if I want to find out that, I have a coordinate transformation, which is basically this, that I can do it for the, so let me write it down for the right exterior, which just becomes tan hyperbolic pi of, and then what I'm going to do is I'm going to say that this shaded region here, okay, maybe let me put some other color. So this yellow region here is described by some other coordinates which are y, okay, and the relation between x coordinates and y coordinates is given by this. So it's just by beta, and that's it. So this is the relation that you have to use. Okay, and if you use this relation, what you will find is that in the y coordinates, the solutions look as follows. They are minus 4 pi squared by beta squared dy plus dy minus divided by sine hyperbolic square pi by beta y minus minus y plus And then similarly, you can do this transformation on the dilaton, and the dilaton will also change, and that dilaton will look like 2 pi phi r by beta into cot hyperbolic of pi by beta y minus y plus, and this is the solution. Okay. So first of all, I have the solution for the dilaton and the patches everywhere inside the ADS2 region of this diagram. So the ADS2 region inside this diagram, I know how to describe everything, and the way I can describe it is by doing this. So the only part of interest here is the really the gray region. Okay, in the gray region, if I know how to describe everything in the gray region, that's the only relevant part, and everything else is just for bonus. Okay, so if you look at this Poincare patch, there's a very nice. So this is a solution of the JT gravity, and the lower box is also a solution to the JT gravity, but they're just related by some coordinate transformation. All right, and if you just look here, what really happens is that when y I think when y plus goes to infinity, x plus goes to 1. Okay, so let's take the other limit, which is y minus goes to minus infinity. That is when x plus goes to minus 1, and that's where this line here is y minus goes to minus infinity. Sorry, y plus goes to minus infinity, right? Because tan hyperbolic at minus infinity will go to minus 1, and hence x plus will go to minus 1. And then this above line is where x minus goes to 1, and that is when y minus goes to plus infinity. Hence, y minus at on this line, y minus goes to infinity. Okay, so how do I draw this? So that means y plus goes in this direction, and y minus goes in this direction. Okay, so this is the construction I have. All right. So maybe, okay. So let me tell you what I'm going to do in next lecture, and that is, yeah. So I'll write down equations in next lecture, but let me just try to tell you what is going to happen. So this space-time which I have constructed here, this space-time can be completely embedded in a 2D flat space-time. Okay. So what does that mean? That means that I can take a 2D flat space-time. All of this diamond that you see is a conformal compactification of 2D flat space-time. And the only relevant part which I want to embed is, you see the gray and blue region here, Okay. And so the part here, let me just draw the white with white boundaries. If you see the part here, maybe white is not good. I don't know. Yeah. So let me draw it with red boundaries. So this part here is the region. So I'm just drawing the boundary of the region. This region here is the region that we wanted to construct. So if you look at this diagram here, it exactly constructs the same region. And this manifold can be embedded in this whole flat space. Okay. So what do you have to do? You have to start from flat space, and let's call that flat space to be some dw plus and dw minus, and then you can do some conformal transformation plus wild transformation. So you can do some conformal transformations plus wild transformations to get to the metric that I had written down before, which is 4 pi squared by beta squared dy plus dy minus divided by sine hyperbolic square pi by beta pi minus y plus this. So I can start from this metric, and I can do these two conformal and a wild transformation to get here. Okay, and that's what I'm going to do. And so this metric here only describes the gray region. Okay, it only describes the gray region. And then what I have to do is I have to also say that this bath, okay, is described by some coordinate, metric which looks something like this, dy plus dy minus. Okay. And now what I have to show is that along this line, where I connected the bath, all fields are continuous. All fields behave nicely, the metric is smoothly connected, and I can take care of wild factors everywhere. Okay. So once I do this, if you just take constant time slices of my flat space, which are these, right? So just take constant time slices. These time slices are basically nice slices for my this hybrid model. Okay, so I'll do it. I'll construct this mathematically next time. I'll just stop here, and please, if you have questions to ask.
Yeah, Rohan has a question.
Yes.
Did you say in the blue region you're going to fill it with some CFT? I just missed that part.
All of the regions. So the whole manifold that we have constructed, we'll put CFT everywhere.
So the gray region is just usual gravity. Even that will have CFT, you'll say.
Yeah. So CFT will be freely CFT. Yes.
The full bulk you're going to fill with 2D CFT.
Yeah. Exactly. My CFT will be freely allowed to go from blue region to gray region to yellow region and everywhere, wherever it's causally allowed to go.
And this is the CFT which you said had like C degrees of freedom.
Yeah, exactly. This is the CFT that has C degrees of freedom. So this is the CFT which whose contribution is hyped up so that over which I can ignore the graviton contribution, but it's not hyped up enough to cause a backreaction.
So you only take the Shortzian pieces coming in Rosca effect and stuff.
Yeah.
Okay, thanks.
Okay.
So this CFT is interacting with the line of the Shortzian modes in between, no?
No. That is CFT1. If I'm putting a CFT on this manifold, or if I'm putting CFT on the this manifold, I have to put a CFT2.
Yeah, but yeah. So I'm saying the CFT is interacting with the CFT1, right?
Oh yes, it is.
And isn't that like introducing a defect into the CFT or something?
I mean, that interaction basically describes what it means by a transparent boundary condition. Right? So if you look at the 1D point of view, what is it? In the 1D point of view, so let's say if I'm saying that in the 2D point of view, which is the above diagram, there is a CFT living everywhere. Okay. Now, if I translate that to lower diagram, the CFT2 is only in the blue region. Okay, and all of the bulk is been just reduced to these two purple lines. Okay, what does that mean? That just means that there is a CFT1 living on the line and there is a CFT2 living on the half line, and both of them are interacting with each other.
Okay, and now these are in this picture it's decoupled.
I mean, left and right is always decoupled, but the left CFT1 is interacting with left CFT2, and the right CFT1 is interacting with right CFT2.
Yeah, so in this picture,
but
it
the
seems like...
Go on, sorry. In the holographic dual, there is no CFT1 because you have replaced CFT1 by the bulk. So in the holographic dual, which is the above diagram, there is no CFT1. There is just gravity in that patch, but there is CFT2, which is freely allowed to come in.
But I'm just uncomfortable with that really flowing. I mean, leaking into the bulk.
I mean, so if you take a, let's say in ADS CFT, if you want to describe, so if you take a CFT Lagrangian, that is dual to the gravity Lagrangian. But now if you want to also describe gravity plus some scalar fields, what you have to do is you have to deform the CFT with some single trace operator. So you have to deform the CFT also. And that deformation, which is just coupling your CFT to a single trace operator, is equivalent to putting scalar fields in the bulk. Okay, and that's an interaction. That's some external interaction that you have to couple your CFT to some external operator. Okay, so once you do that, then the bulk, the holographic dual starts describing gravity, but also some fields riding on that background. And that's exactly what I'm doing here. I'm in the lower picture. I have a CFT1 coupled to something, and that coupling in the top diagram will basically become gravity plus fields in the middle portion in the ADS region, and then there was already a field living outside.
So can I just repeat what I understood just to make sure?
Yes.
Yeah. So I thought the CFT2 we are considering is like some Gaussian point CFT of C scalars. Is that right?
CFT2 we are considering is no, we won't be considering that.
I didn't understand how did you say the coupling?
Yeah. So that matter which I had written down is what is to be understood as CFT, but I had just written and CFT2 exactly. But
now you are like so now you want to I didn't understand how do you fill up the bulk and with those scalars now and call it same
maybe
as
let me write
CFT.
down some equations here,
Okay.
So if you have a action which looks like root gr, okay, that is dual to some CFT action. Okay, this is a part of the duality. Now, if I want to say I have root gr plus some scalar fields on it, okay, if this is true, then I have to, on the right hand side, I have to modify this with CFT2 plus some source with a single trace operator. Okay, this is the modification. So this part here, somehow in the dual description becomes a scalar field in the bulk. Okay, and the relation is the scalar field in the bulk as it goes to r to infinity. Okay, so maybe I should write r to the delta minus. This object has to be identified with j of x. So this is ADS. This is what ADS CFT says. Okay, so what you have to do is
okay. So now I'm just confused. Do you also now equate the delta phi system, the delta phi whole square, the side scalars, fields, and SCFT? Do you identify these guys?
Do I? Sorry.
Is the SCFT also now? Do you at next step would you also say the SCFT is also like the same scalars? Which
No. So this is the picture where the equations have written down are equations valid without attaching the bar. So forget about the blue region. So if I don't want the blue region, forget about the blue region. Then what is the first of all, one theory is the holographic theory where you have a line. So all I'm drawing is t equals to 0 slice. Let's say. There's a t equals to 0 slice here. Okay, and I'm drawing that. The holographic dual to that slice is basically two dots. And now let's say this is SYK, this is SYK, or any CFT1 that you want, but I don't know any CFT1 which has a dual.
I think I'm comfortable
and then this is JT.
Go on.
All right. Now I want some fields also on this JT. Okay. How do I get this field? That means I have JT plus some fields. Or JT plus matter.
Yeah, that's a single trace deformation. All that I understand. I'm just confused about when you say.
I'm saying in general, if you want to put something other than a scalar field, right? If you want to put something other than this, you have to do a more complicated deformation. You don't have to do. You can't. Single trace deformation won't give it to you. You have to do some very complicated deformation, and so you just assume that you do this deformation, and then that deformation should be equivalent to putting a large CFT2 on the bulk.
I'm just uncomfortable about like extending the CFT2 in the wedges towards onto the full diamond.
No, it's not extending. That's what I'm saying. So first of all, think of this picture where you have CFT1 plus singleton's deformation that is equal to JT plus some fields. Okay.
Yeah, I'm cool with that. Okay.
Now attach baths to both the systems. So it's SYK plus deformation plus attach a bath to it, and that is equivalent to. So you just replace SYK plus deformation by JT plus fields, and then again attach fields to it.
Yeah.
Right.
Okay.
And that's it. That just creates this. Maybe I'll try to explain this more in the next lecture, because I think I'll have to write down more equations.
Okay.
Yeah, Adwait, just a quick follow-up on that point. So when you're extending that statement now to say that it's JT plus fields plus something else is following that equality line which you put up, the correspondence line, the normalization condition is going to get a little different, right? I mean, obviously, because now how are you defining the condition for this, that the coupled sector in terms of what does it become on CFT1?
Well, the boundary value. So at least in the case that we know, where you do single trace deformations, what you know is that the source by which you deform the CFT, which is J of X, has to be matched with the boundary value of the field from the bulk. So when you attach an external field to field, which is the blue region, all you have to do is you match that value at the boundary. You just match the boundary value coming from the bulk and boundary value of the field coming from the path and identify it. That should give you the transparent boundary condition.
I see. So that is the matching that is taking place.
Oh yes, yeah.
Okay, fine.
Adwait, is so in the bottom picture you will basically have a boundary CFT, right? Like a BCFT, where it's a two-dimensional BCFT with one-dimensional on the one-dimensional boundary you have sources and dilettante or whatever, JT gravity. But there is
more generally, you would say that it's a 1D CFT coupled to a 2D CFT.
Or a 2D CFT, which is a boundary CFT, where on the boundary there is a 1D CFT with sources, which source the 2D CFT, something like that.
Yeah. So I mean, there is a question about whether 1D CFT can be directly approximated as boundary. I mean, can be directly approximated as a boundary state. So you can say that all of this setup is basically a 2D boundary conformal field theory. But I'm not sure about that. But maybe it happens.
And the gravitons are simply not active in the blue region.
No, there is no gravity in the blue region.
Okay.
Okay. All right.
Okay, I think we should thank Adwait for his wonderful lecture. So since it's already 13 minutes past 6, let me stop the recording.